at Politecnico de Milano, a doctoral student, and the Universidad de los Andes. He has a mechanical engineering degree for Universidad EAFIT and a master's degree in mechanical engineering from Universidad de los Andes. He has worked on various research subjects related to industrial digitization for the last 3 years. Such topics include intelligent maintenance, data analysis, and cyber physical systems. His research trajectory has led him to research the integration of digitalization technologies into asset management. David has assisted in multiple universities courses in mechanical engineering throughout his career, focusing on digitization in machinery dynamics, intelligent maintenance, and using data processing and visualization tools in CAD, CAM, and CAE file. He is author and co-author of several publications related to digitization published in international scientific conferences and journals. I welcome him to the conference. Go ahead, David.
Hello, my name is David Sánchez Londoño. I'm a student at both the Universidad de los Andes and the Politecnico de Milano school. I'm doing a double degree PhD on asset management. And so, well, I think let's get started. Please let me know once you are able to see my screen, or actually, I think I can see this. Yes, I suppose that you can see my screen now. So yes, today I would like to give you all an overarching view of smart retrofitting, what it is, and how it has affected the way maintenance and asset management is performed. But before all that, let me tell you a little bit about myself. So as I mentioned, I'm a doctoral student at the Politecnico de Milano and the Universidad de los Andes. I got my mechanical engineering degree from Universidad EAFIT, where I was part of research on data processing and visualization tools in computer-assisted design, manufacturing, and engineering field. I then went on to get a master's degree in mechanical engineering from Universidad de los Andes, where I studied the flow of data and information from shop floor machinery to data and information analysis systems. Now, during this time, I've worked on various related research subjects, such as intelligent maintenance, data analysis, and cyber physical systems. So today, I am undergoing a PhD degree in both Universidad de los Andes and the Politecnico de Milano, focusing towards the integration of digital transition technologies, Industry 4.0 technologies, into maintenance and asset management. Now, this brings us to the topic at hand: smart retrofitting in maintenance and asset management. So today, we live in an industrial landscape where production organizations must leverage the capabilities of data analysis and digital technologies to stay relevant in a field that becomes more competitive every day. So the ability to optimize operations and maintenance of our systems by analyzing real-world data is becoming less of an option and more of a necessity, especially in a world where production companies are expected to deliver better results while spending less resources. Because not only all industrial machinery is able to natively work in this data-heavy environment, companies today are left with two choices. They either replace their most critical industrial equipment with digitalization-enabled machinery, or they can retrofit their existing machinery with the capabilities that are required to work in this data-heavy environment. Now, oh no, wait. So before I discuss retrofitting by itself, I think it's important to introduce what I just showed you, the different maintenance strategies that have existed throughout the years. Now, some of you might already be familiar with this, but I think it's important to make a quick overview because the evolution of technology and maintenance is so deeply connected to the evolution of strategy that it doesn't really make sense to talk about the technology without strategy. So with that said, let's start from the beginning. So the maintenance strategies have evolved from the first ever since the first industrial machines required any sort of repair, right? So a long time ago. And these strategies have matured from simple corrective actions to more complex strategies. So the first of these strategies used to maintain machinery is reactive maintenance. And in reactive maintenance, we handle failures once breakdowns occur, right? So this means that machines operate until they fail. and at this point, they are repaired, if possible, or replaced with new machinery. Now, this strategy can lead to the unexpected machine downtime and high economic consequences because of the cost and the resources that is associated with repairing machinery that fails unexpectedly. So as time went on, engineers realized that for the most critical machines, they couldn't simply afford to just let them fail. So plant maintenance was born. Now in plant maintenance, we have an association with maintenance actions and periodic intervals. So these intervals can be time-based, so we will perform maintenance every 25 days, for example, or they can be usage-based. So we will perform maintenance every 200 hours of operations, which can be 10 days, 30 days, and anywhere in between. So this can prevent failures by identifying and correcting deterioration before it becomes a fault. However, it is unable to detect random failures that don't follow this as time goes on, it fails pattern, right? So it also has the issue where we perform maintenance actions preemptively on the equipment, and these actions might not actually be needed. So we might be wasting time and money performing maintenance actions. So to deal with this sort of shortcomings, proactive maintenance was, let's say, introduced. So in proactive maintenance, we may aim to predict failures by monitoring the real conditions of machinery. So this, in theory, allows maintenance engineers to schedule maintenance actions when they are needed, rather than at fixed intervals. So condition monitoring is made possible by acquiring data from the monitored machine and analyzing said data. So this enables estimating the current state of machine without stopping the machine, which is a very great advantage. And it also allows for the prediction of the future state of the machine, of the health state, for example. Now, this estimation and prediction capabilities go hand in hand with various maintenance concepts that aim to learn from previous failures through the life of operating systems. So, for example, we have reliability-based maintenance, we have reliability-centered maintenance, total productive maintenance, failure mode and effects analysis, and all of these aim to focus on improving reliability. And these are some very important steps in the evolution of maintenance management. But there's still one piece that is missing. There is one small problem here. And the fact is that the main goal of maintenance, ever since maintenance was sort of created, has been to optimize maintenance performance, which of course makes sense at first glance. Now, this means that the maintenance department of an organization will do everything in its power to keep reliability of assets high, which might sometimes clash with the goals of other departments. So, for example, this might clash with the goals of the production department, which doesn't want high reliability. They just want high throughput, right? Even if it means less maintenance actions. And it might even clash with the objectives of the organization. And so that is where our final maintenance strategy comes in, which is strategic maintenance. Now, strategic maintenance adopts a perspective of asset management. And what I mean by this is that instead of focusing on increasing asset reliability, asset management aims to realize value from assets in an organization. So it exploits assets towards achieving organizational objectives. Now, this means that instead of, for example, focusing on reducing the maintenance costs of systems, or increasing their reliability and their maintainability, in strategic maintenance, we actually consider maintenance as just one of many processes that are involved within the asset management landscape. And so here, management decisions are made considering the impact they will have on the entire management process, not just maintenance. And what this means is that maintenance is not considered in isolation anymore, but instead it's considered as a part of the whole organization. And in this context, the conflicting goals of these multiple departments, so operations, maintenance, and so logistics, and so on, they must be balanced to obtain a solution that is in the best interest, not of one single department, but of the organization as a whole. So any maintenance decision that increases maintenance performance, but for some reason decreases the overall organizational performance, such as excessive planned maintenance, for example. Such a decision would be discarded under the strategy of strategic maintenance in order for decisions to more closely follow the organizational objectives. Wait, why doesn't, okay, here we go. Now, so back on topic. As I mentioned earlier, this evolution of maintenance strategies is actually parallel to the evolution of maintenance technology, which is actually our focus for this talk. So what happens is that technologies such as cyber physical systems and the Internet of Things, they have led to this trend of automation in the manufacturing industry. Now, this trend has a lot of names. It's been called the fourth industrial revolution. It's been called Industry 4.0. It's been called smart manufacturing. And all of these, they are slightly different. They might have slightly different meanings, but they're usually used interchangeably. So for the purposes of this talk, I will actually be referring to something called the digital transition. So because rather than a discrete revolution that can be pointed to a specific point in time, which is usually said to be 2011, I see it more as the last few decades having brought the adoption of multiple technologies into the production landscape, bringing this sort of gradual transition to a smarter industry. But just keep in mind, when I say digital transition, you can think of Industry 4.0, you can think of smart manufacturing, think of whichever term you are most familiar with. Now, this digital transition actually involves a vision of enabling transparency. What does this mean? It is the ability, it is the ability to measure the actual manufacturing capability of a system and measure and reduce uncertainties. So, for example, the planning of actions in a manufacturing system often assumes that machines have perfect availability. And they also assume that they have perfect performance. And the problem with this is that when machines fail, because they will fail, or when they produce at less than perfect efficiency, replanning processes have to take place. We need rescheduling processes occur. However, thanks to transparency, the real availability and the real performance capability of these manufacturing systems can now be measured. And this information can be exploited in the planning of operational and maintenance actions. Now, manufacturers can quantify this information, which is usually invisible, through the exploitation of these digital technologies of Industry 4.0 and the realization of transparency. Now, in general, this sort of insight into the real state of machinery enables optimization of existing manufacturing processes, one of them being maintenance. And in particular, increasing increasing the transparency in manufacturing through these digital transitions enables the rise of the two last sort of strategies of maintenance that we discussed, which are proactive and strategic maintenance. Now, in the case of proactive maintenance, a transition towards digital means enables failure prediction. So many failures can be predicted in a machine by monitoring and analyzing its physical conditions. Now, this failure capability is enabled by data analysis processes that can extract useful information from data that is collected by sensors in machines. And it allows for maintenance actions to occur just before failures occur. On the other hand, we have strategic maintenance, which can benefit from transparency by quantifying the contribution that maintenance brings to organizations. So all the decisions made in strategic maintenance actually intend to fulfill the maintenance functions, but most importantly, supporting asset management or organizational objectives. And because of this, all maintenance decisions actually have to consider organizational objectives. So once maintenance decisions are made and the resulting actions are executed, the contributions of each specific decision can be evaluated through this increased transparency so that further decisions can continue supporting asset management. Now, I've been talking about maintenance strategy, I've been talking about technological evolution. So where does smart retrofitting come in all of this? Well, now that we're on the same page regarding maintenance strategies and how technology has evolved alongside these maintenance strategies, we can discuss smart retrofitting itself. So as I've mentioned, digital technologies have to be integrated into manufacturing devices of a company to be able to exploit the benefits of transparency. Now, for devices that do not have these capabilities, they must be A, replaced, or B, upgraded, so that we can enable this transparency in machinery. Our focus now turns to the second option, which is upgrading, taking machines that do not have capabilities required for this digital transition for Industry 4.0 and adding said capabilities. And this upgrading process is what we call nowadays smart retrofitting. So what is smart retrofitting exactly then? Well, smart retrofitting has been referred to as the integration of new technologies into legacy systems to enable the digital transition. Now, with legacy systems, we refer to quote unquote old equipment, right? So this equipment that doesn't have capabilities required for the digital transition. And so smart retrofitting is this action that aims to transfer the requirements of the digital transition vision to legacy machinery, using the lowest time and lowest capital investment that is possible. And so when we talk about smart retrofitting, we should be focusing on identifying these capabilities, these requirements, and figuring out how to enable them in machinery that do not have them. Now, more formally, smart retrofitting in maintenance refers to the development of maintenance services through the retrofitting of legacy devices with these following functionalities: data collection, data communication, and data processing. Now, this definition comes from a review on existing smart retrofitting literature. This review is still not published, but it should be published in the coming months. So for anyone that is interested, you can look for this document in the coming months. Now, let's look at each of these components individually. So this refers to the capability of machinery to transmit sensor data within a network to either local actors or to remote actors. Now, such communication occurs in systems like this one over here. Now, M2M stands for machine network. Now, legacy devices, unlike M2M machines, which actually, let me use the laser here. So legacy devices, such as this one over here, they are not capable of communicating directly to a network and must undergo smart retrofitting. Now, M2M gateways, which are sort of, we can call them bridges conceptually. And so these gateways then enable M2M communication capabilities for legacy devices. Now, all of these devices will communicate with a server, which can be local or exist remotely, perhaps in the cloud. And this server aggregates data, or rather has to aggregate data from multiple sources in a single location. Now, of course, alternative configurations are possible, right? This is only just one example of how a machine-to-machine network might look like. But the constant here is that the isolation in which legacy machinery operates has to be removed. Legacy machinery has to be able to communicate with either other machines in their system or at the very least with a main server. Finally, smart retrofitting involves data processing and analysis. Now, this refers to the capability to transform sensor data into information and knowledge through data preprocessing, visualization, data analysis. And now these steps, they can take place directly in the M2M devices, in the M2M gateways, or they can take place in the local server, as I mentioned earlier, or they might take place in a completely different server. somewhere in the cloud. It can be either local or it can be remote. There really isn't a specification on where data processing has to occur, but it is a constant that there has to be some sort of data processing to take data and transform it into information. Now, once a device has enabled data collection, communication, and processing, it is possible to develop smart maintenance and asset management services that exploit the data that has become available and the information that has become available. Now, these services include, but they are not limited to, actually, just give me one moment. There we go. Now, these services, some of these services are fault diagnosis assessment, prognosis assessment, and health management. So with fault diagnosis, we mean just identifying or at least estimating the current state of devices. With prognosis assessment, we mean not identifying the current, but rather predicting the future condition, the future state of devices. And finally, we have health management, where we take this information, so the current state and the predicted future state, and we use this to bring decision making. So I would like us to look, actually, let me just go back, but I would like us to take a look at maintenance strategies again. And why do I do this? Because I think the best way to actually see how, now that I have shown what smart retrofitting is, how it's defined in literature, I think that a way to understand better what it is, how it's being used, is actually going through the different maintenance strategies and see how each of these strategies has exploited or can potentially exploit the advantages that are brought by smart retrofitting. So now back to the slide. Let's start from reactive maintenance, the first strategy, maintenance strategy that we saw. And as you know, this strategy actually involves taking maintenance actions after failures occur. So in this case, rather than enable failure detection or prediction, what smart retrofitting does here is that it can be used to enable machinery to remotely alert the relevant stakeholders to failures that occur in the system. So for example, to the maintenance manager, to the equipment owner. And this can be detected, for example, it is usually detected by PLCs. Now, this automatic, not a posteriori, to say it away, after the fact, failure notifications, they have the potential to lead to automatic scheduling, automatic rescheduling of maintenance and production activities, which now consider this new state of the system, these failures that have just occurred and have been detected. The next maintenance strategy, which is of interest here, and that we will see how smart retrofitting acts on it, is plant maintenance. So within this strategy, just a moment. So within this strategy, smart retrofitting provides transparency. It lets us see what was usually impossible to see. In this case, it lets us see the operational states and the operational modes of machinery through time. Now, what do I mean with this? So when we talk about operational states, we refer to the level of activity that is occurring within a machine or a system. Now, these are commonly described in terms of just being either on or off, relatively simple. On the other hand, operational modes, they can be a little bit more complicated, a little bit more abstract. And these are user selectable, or rather operator selectable sets of activities that perform a specific task. So for example, instead of just being either on or off, a machine might be initializing, it might be calibrating, it might be configured, cleaned, it could be idle, it could be producing, it could be in the process of maintenance, it can be in any number of operational modes. And insight into these states and modes, there we go. Insight into these states and modes of machines actually permits users to measure the operation time of specific machines and to measure the time that machines spend in any given specific operational mode. So the maintenance time, the idling time, and so on. And what this does is that it increases, by increasing this transparency and allowing us to know what the machine is doing through time, we are able to perform better plant maintenance. Plant maintenance that is based not on operational time, or rather plant maintenance that is based on operational time. An Excel sheet, in a document, and so on. But this increased transparency, this is smart retrofitting, and in general, the digital transition allows for this information to be collected and later analyzed automatically. Maintenance strategy that is perhaps one of the booms of the current time. So after planned maintenance, we have proactive maintenance, right? Which a lot of you might associate directly with condition-based maintenance, with CVM. And this is by far the most cited maintenance strategy in literature when it comes to smart retrofitting and just cyber-physical systems in general. Now, here, the capabilities added by smart retrofitting are exploited by enabling the services that we discussed earlier, right? So fault diagnosis assessment, prognosis assessment, and health management. These are made possible more so than in the previous strategies by advanced data analysis algorithms that turn raw sensor data into decisions, what, again, is usually known as condition-based maintenance. And the overarching process looks something like this. So first, we have a criticality analysis, which identifies the components, the failure modes, and the effects that are the most relevant, as the name says, the most critical, and which should be maintained through condition-based maintenance methods. Now, once the critical components of our system are properly identified, the three main capabilities of smart retrofitting are used. So data collection, data communication, data processing of the data that was chosen in the criticality analysis. And now, remember, if any of these three is not available in a given machine, it's the job of smart retrofitting to enable these capabilities so that the services can be exploited. And speaking of the services, this sequential process of data collection, communication, and processing ends with the availability of information about the system, which can be used and are used by services to facilitate decision-making. Now, this procedure has been extensively used in academic literature, with the analysis of rotating machinery, for example, being especially prevalent. So the analysis of rolling bearings, the analysis of engines, the analysis of pumps, and so on. It's very prevalent through literature to have smart retrofitting in such systems. Finally, we arrived at strategic maintenance, which, as we have discussed before, is directly related, hand in hand with asset management. Now, being the most recent maintenance strategy to be created, the involvement of smart retrofitting it's still not extremely clear in literature. So conceptually, an intersection of strategic maintenance and smart retrofitting can result. So if we look at this part over here, so this intersection can result in the intelligent selection of which machines in the system should undergo retrofitting. Now, this answers one of the main questions that are made when someone encounters smart retrofitting for the first time. When I have a specific machine where we want to enable transparency, right? We want to enable all of this Industry 4.0 services, these digital transitioning services. So we have a machine and we want to do this. Should I retrofit or should I replace, right? So this is an open-ended question. Management, smart retrofitting, where asset management, let's say, supports the decision of performing or not smart retrofitting. We can also go the other way around, which is the second part of the diagram. So once a machine has been retrofitted, in theory, it becomes as capable as any other cyber-physical system, right? So that is why we have cyber-physical system here. And so the open question changes a little bit. So rather than asking how can smart retrofitting aid asset management, we ask how can the digital transition or Industry 4.0, smart maintenance, smart manufacturing, how can these support asset management processes? How can these support and improve decision-making in asset management? And then once we know how the once we have studied how digital transition can support asset management for a specific scenario, for a specific organization, for a specific type of asset, then, and we take this back line over here, then we can go back to identifying if replacement or retrofitting is the best answer to enable the required transparency in these systems. So as you can see, this, let's say, collaboration between asset management and smart retrofitting, it can go both ways. So now that we have a rough understanding, first of all, of what smart retrofitting is, right, a sort of definition, and now that we have explored how it has been used or how it could conceptually, theoretically be used in different maintenance strategies, we can consider the benefits of smart retrofitting. Now, keep in mind that the goal of smart retrofitting is to enable services that are only possible due to the existence of data collection, communication, and processing, or in other words, to enable services that are only possible due to the increased transparency of systems, which are brought by the digital transition or Industry 4.0. Now, what this means is that most benefits of smart retrofitting are pretty much analogous to the benefits brought in general by the digital transitions, which with, of course, a few exceptions that are unique to smart retrofitting. And such benefits, they can be classified into three categories, which are actually taken from asset management, which are performance, costs, and risks. So first, the introduction of digitally enabled services can increase the performance of a manufacturing system. It can optimize the production capability. This is possible, for example, by improving the availability, maintainability, and reliability of the physical assets of a given manufacturing system. The second way in which smart retrofitting and in general digitalization can be an advantage to organizations is through cost, and specifically the reduction of costs. So this occurs for both capital costs or CAPEX and for operational costs or OPEX. Now, regarding capital, the improved maintenance performance usually translates into, let's call them, longer lasting devices that can be replaced or less frequently. And in the particular case of smart retrofitting, the capital cost associated with replacing machinery can be reduced or it can be completely avoided. Now, regarding operational costs, literature shows that the digital transition, digitally transforming assets is able to reduce maintenance costs, thanks again to improved maintenance performance, and that maintaining assets in a healthy state for longer can actually reduce losses due to reduced performance, to reduced efficiency, and misuse of resources. And third, last but not least, risk or uncertainty. Now, thanks to smart retrofitting and again, in general, digitalization, digital transformation, risk or uncertainty can be more properly managed, thanks to the increased information, to the increased amount of information that becomes available. So when information is made transparent, there is less uncertainty, right? There is less uncertainty about how machines operate, and better decisions can be made. And besides this operational risk, other perspectives of risk are affected positively, right? Not just production risk, but for example, human risk. So by automatizing maintenance processes, humans can be removed in some places, of course, not everywhere, but humans can be removed from the maintenance loop, specifically in situations where the health and safety might be compromised when performing maintenance. And the improved maintenance performance that I mentioned before, it also results in reduced risk for the environment, since it is known that improper maintenance can bring environment difficulties. It can bring hazardous emission. It can bring increased consumption of spare parts and generate production wastes. Now, whenever there are advantages or drivers, as we call them, there are also challenges, and smart retrofitting is not the exception. And so the challenges associated with the wide implementation of smart retrofitting, which in a way could be considered as potential avenues for research, for ongoing research, they can be roughly divided into technology and industry gap. So first, there exists a technological challenge in how to properly implement smart retrofitting. So whether it is an asset management scenario or a maintenance management scenario, the challenge exists. And the matter of how to properly extract data from systems that still retains the required levels of quality, the required levels of performance at competitive costs is an ongoing issue. When dealing with data communication, on the other hand, the matter of how to transmit very large volumes of data, big data actually, associated to the digital transition, while still maintaining proper levels of cybersecurity, is also an ongoing issue. And finally, regarding data processing, the matter of how to efficiently and effectively transform sensor data, raw data from the shop floor into useful information that eventually allows for decision-making is the subject of constant research. It has been for many years, and it will be for many years more, because a lot is still not known in this area. Now, regarding the industry gap, there exists a gap between industry and the academy, right? So after data collection, communication, and processing takes place, well, the fourth step of smart retrofitting would be services. And in this case, we require industry-focused services. And the problem here is that, at least from the eyes of many industrial actors, there is this gap between what has been researched in academy and what has actually been implemented, or rather what has been created in an implementable form for the industry. So to be specific, the conversion of information, right? So information about our production systems, converting that into decisions, right? So because it's one thing to know the condition and future health of all of my different assets in a factory, but taking that and turning that into specific actionable decisions is an area of research that still needs a lot of work. And specifically, there is a lag where this potentially has been researched in academy, but it has not been properly implemented in industry because of, well, not the lack of cooperation, but because of an opportunity for more cooperation between the industry and the academy. And Let me put that in another perspective. So organizations that implement technological advancements in their processes can be classified into technology push or demand pull. Now, technology push companies are those that implement the newest technologies without a clear understanding of how these technologies will disrupt the market, of how these technologies will benefit them, in the hopes that just the fact of being technologically advanced will be enough to be an advantage. On the other hand, demand pull companies first identify what the real needs of stakeholders are, and only then they go ahead with identifying and deploying technological solutions that will give them a competitive advantage. Now, although we can sometimes be infatuated by innovation for the sake of innovation, it has been found that it takes longer for technology push companies to start earning revenue when compared to demand pull companies. And interestingly enough, many companies that start as technology push eventually have to switch to demand pull strategies to continue operating profitably. So what I'm trying to say is this: it is imperative then that when undergoing these digitalization advances in the academy and in the research sphere, in particular regarding smart retrofitting, efforts should be made to take a realistic, industry-focused approach, where concrete tools and solutions are created not just from an academic perspective, but for industry-ready scenarios. Tools that fulfill the real data collection, communication, processing, and decision-making service needs of the industry, rather than only advancing technology for the sake of advancing technology without a real industrial perspective. Now, this is a perspective that all the institutions participating in this graduate pre-workshop have taken to heart. They are some of the industry leaders in advancing the real-world industry-focused implementation of smart retrofitting and of the digital transformation of manufacturing. And so, yes, this is my invitation for all of you for the rest of this pre-graduate or pre-workshop, let's say, for this pre-workshop, and for the rest of the workshop, for those who will be attending. Always think of the industrial implications of research. Always think of how research connects directly to the needs of the real industry, because at the end of the day, this is the job of research, to advance the industry. And so that's it. That is what I wanted to show you, just a little overview of smart retrofitting in maintenance and asset management, perhaps to prepare you a little bit for the presentations to come. And I hope it is of use to all of you. So I think we have a couple of minutes left, so maybe 1 or 2 minutes. So if there are any questions, I will be happy to discuss them, or otherwise, thank you all for listening.
Thank you, David. So I don't know if there is some question.
So thank you very much for your presentation, David, Tocayo. So looking forward a little bit more into the research, a lot of the smart retrofitting strategies that you mentioned are, let's say, how we connect and how we extract data from the machine and how we analyze it and so on. Is there any smart retrofitting strategy for better human-machine interfaces? Because of course, you know, it's not only the PLC and how we get the data and how we process it, but also how we interact the data for such new digital maintenance, assets management services that we want to take advantage of smart retrofitting the equipment. So any thoughts on that, on how we also can retrofit HMIs of the old machines?
Okay, perfect. Well, thank you, David, for your question. This is a very good question, especially considering let's say, the course that smart manufacturing is taking towards what we might call the operator 5.0, right? So this sort of holistic integration of not just technology into the manufacturing process, but of humans with the manufacturing process and these technologies. And this goes very much in line with specifically the implementation of smart retrofitting in the, let's say, strategic maintenance domain. And why is this? Because from the perspective of the strategic maintenance and in particular asset management, I didn't go into much detail about this, but one of the focuses of asset management is that is to take a holistic approach, a value-based approach, where we don't simply care about, let's say, money or economical gains, but we have a sustainability perspective. And one of the main pillars of sustainability is the person, right? The social sustainability. How does the human, how do communities of humans integrate with this entire process? So I think that the operator 5.0 and studying specifically how all of these technologies can directly enhance the abilities of the human. I think this is a very interesting and very novel, let's say, course of research right now, because as smart as we can get these services to be, at the end of the day, these services end up providing support for the human. At the end of the day, whether it is in decision making, whether it is in performing complex operations, at the end of the day, it's the human who has to be at the center of it all. So smart retrofitting ends up being a support for digital transformation, and as I was saying, one of the main components of
How are you? First of all, thank you very much. It's a very interesting presentation, a very interesting research. One of the things that I found really interesting, I'm sorry to say it all, was the gap success case of any company that has applied smart retrofitting, or any case study that you saw that any company successfully applied this smart retrofitting approach or the strategic maintenance approach and had and strive the goal that you're looking for.
Thank you very much. Sorry, I can't really see like the screen or the audience. What is your name?
My name is Juan Sebastián Villegas.
Okay, Juan Sebastián. Thank you, Juan Sebastián, for your question, and I think it's a pretty relevant question, and it makes me, well, I don't want to say a little thoroughly searching. Of course, we are humans, and we can always miss things, but through the 5 or 6 months that I did the necessary research for this smart retrofitting, let's say, over, didn't see any strong successful case, right? It's a successful case where the industry in robotics. But the common denominator among all of these, let's call them success stories, was that when choosing between replacing and retrofitting, they replaced, right? And the problem here is that this replacement, it takes a very large, let's say, capex investment, a very large capital investment, which means that there is currently this whole revolution ongoing, this fourth industrial revolution. There is this deep change in which manufacturing occurs, and only the largest companies are able to exploit this change, because small and medium enterprises, or SMEs, that might not have the, let's say, the economic backing to take their entire fleet or a part of the fleet and replacing it with digitally capable machinery, they are left out of all of this great research that is going on. And that's where smart retrofitting really has the potential and the need to act. But right now it is a potential, right? Because this potential has not yet been realized. So the reasons why it has not been realized and what we can do about it, that is part of the ongoing conversation, of the ongoing research that is going on today.
Okay, thank you, David. So thank you very much for your speech. And we can go on with the next one, which
thank you.
is going to be the speech here now in person. So we are going to switch. And I leave the floor to Maria Jose for the presentation.
Yes, we welcome to Juan Fernando Villegas. Juan Fernando is expert in data science, machine learning, and IE forecasting and foreseen events with advanced data analytics. Fracttal is computerized maintenance management system that is having huge success in Latin America that integrate machine learning capabilities. Therefore, it can be used for smart retrofitting. I welcome him into the stage with the conference Quantitative Reliability Center Maintenance using Fracttal plus Predictive, a practical approach.
Thanks for having me. I'm Juan Villegas, and we will talk about what we are doing with Predictive and Fracttal. Fracttal, as this beautiful girl told me, Fracttal is a CMMS. It's on the cloud CMMS. And we, with my team, we designed Predictive. It's a tool to predict, based on reliability, when an asset will fail. So, okay, we're right here, maybe. Okay. So let's talk about a little bit about Fracttal, about our platform. In Fracttal, we have, as I told you, is a CMMS on the cloud, and we have a separate platform that called Predictive, and we are using the data that is inside the CMMS or any other CMMS to make some predictions about the asset life cycle. So let's talk about first what is a prediction and what are the elements of a prediction. So I think the most clear example is about the weather. When you see on the TV or on internet about weather forecasting, for example, you have three main elements about prediction. The first one is what is going to happen. When you try to predict something, it's clearly that you are referring just a specific event. For example, if it's cloudy or it's rainy. But in the case of maintenance, you are talking about, for example, wear out, for example, vibration speed of a motor, for example, or temperature inside an electrical transformer. So you are not talking about anything. It's a specific event. The second element is about how likely. We talk about probabilities. It's the second thing. It's not just a red light and green light. It's just you need to know a number. What means that about? What tells you about the risk? So you can have, for example, 62% or 60. When we talk about maintenance, we talk about reliability as that concept, that talk about risk. And finally, and very important, is when will happen. It's not the same that the weather tells you that the rain will be this afternoon or tomorrow. You take very different decisions about that. And in maintenance, it's the same thing. It's not the same thing that you have 30 days until failure, or if the failure will occur tomorrow. It's not the same case. So you can transform those three questions in that three questions. The first one, when you talk about what is going to happen, you transform it in what I need to be prepared. Will you need more spare parts, more people? So, and what kind of spare parts you're talking about? So it's the first part. How likely you will transform, how much risk can I assume? It's not the same if you have a motor that have an extra motor to work, or if you have two different production lines. If one production lines will run out, you have the other one to work with it. In this case, it's not the same perception of risk. So imagine in other case, if you have an airplane engine, the risk perception is very different. And the one is how long have I to plan and execute, is how many time I have to be prepared. You take different decisions too about that. So the main concept we are working with is reliability. Reliability is the probability of proper operation over the time. We are talking about a specific event. We are talking about a probability, and we are talking about a moment on the time. So we can have a prediction using reliability. The second part is reliability is a key part of some service level agreements. So it's not just a fancy indicator. It's part of a legal issue that could put you in some problems sometimes if you can't achieve the SLA. The third part is RCM. Most of the companies worldwide would like to go to RCM strategies, reliability-based or centered maintenance. If you have a reliability measurement and forecasting, you can have a foundation here to make RCM. And finally, it's a good way to evaluate asset risk. And I can give you a very simple example. What kind of insurance policy should you have? I'm not, just look here. I'm not talking about spare parts or people or corrective maintenance or preventive. I'm talking about the whole company, the whole organization, legal issues, insurance, etc. So let's see this as a cross-cutting concept. For example, if you see reliability, you can see a main indicator that you can use not only in maintenance. You can use it too in financial, legal, production, and maintenance. For example, in financial, if the assets fail, you can run out your budget. So what will be how can you avoid that? Financial provisions. But you only can do financial provisions if you have a good foundations to make a statement of what are your expectations about future failures that can make you incur in extra expense. If we are talking about legal, we are talking about breach of contract, and you can get an insurance policy just to solve that. In production, you can make a production plan. If you are afraid about a production loss, you can make a contingent production, for example, to make a contract with an external industry to solve problem of production loss, for example, or to have two different production lines. So that's very important because until this moment, I'm not talking about maintenance. I'm talking about the whole company. And finally, obviously, maintenance. When you have failures, you have your asset life reduced. So you can use reliability to make a better plan and a better budget. So let's talk about the data. Everybody is talking about machine learning, artificial intelligence applied to maintenance. But the maintenance data is not easy to handle. You have a very big issue right here, is you have few valuable data. Just imagine if you make a measurement, for example, each 5 minutes of some variable. If you see 95% of the time is normal operation. So you don't have valuable data. The data that you need is the data that tells you that something wrong is working inside your machinery. So failures are uncommon events. And that's the real problem behind. Sometimes when you talk about artificial intelligence, you are talking about big data. You need a lot of data, and you don't have right here. So many times, some kind of solution is just put another variables in this equation. Okay, you have only one variable, for example, temperature. Just add pressure, add vibration, add another variables. Many times, those variables are measuring the same event. So you have more data measuring the same thing. And that's a huge problem. When you try to fit a model with more variables, the amount of data required to fit the model grows exponentially. Maybe if you have one variable, maybe you need 100 registers of 100 data. But if you have 3 variables, maybe you need 10,000 or 1,000 registers. And in this case, as I told you before, failures are uncommon events. So the problem is worse. And finally, maintenance data by itself have more context information than you think. Just think in one field of one document, the work order. When you only watch the date, just the date, it's just a date. Any document that you have in maintenance have a date. But when you have many dates, you have a pattern. You have more a date, and you can make a whole conclusion just with that date. And that's an intelligent way to process the data. That's the way that we make. We tried with Predictive to make models with few data, but trying to extract the context information and the patterns inside, not requiring more data. It's the run maybe in the market today. And we can divide into two kind of models to make predictions. The first one is the degradation models. And we call degradation models, and we defined as too critical to fail. Just imagine an airplane engine. An airplane engine never fails. You can monitor some variables, but you never see a fail right there. So that's the first kind. The second kind of models are reliability models that too simple to sensorize. And that means something important. You never see, for example, with the illumination or the light bulbs, you never put a sensor right there to measure how is temperature in the light bulb to predict when will fail and change it before that occur. You simply, you let the light bulb fail and replaced by another one. So in these kind of models that are too simple to sensorize, you simply take dates or to extract patterns from that. And you can make those kind of models. Let's see the first one, the degradation models. Now, I know that this is a good example of a degradation model. Okay, with a degradation model, you typically have a thing like this. That's an IoT system. You are monitoring some variable, for example, vibration speed. And you have the model data, and you have some new data. That's normal until here. I know that you are not seeing nothing really new. The things really new begins right here. We make some algorithm to an stochastic process algorithm to make a prediction. Trying to predict when we'll touch that maximum limit in this case. We can work with minimum limits as well. But in this case, when in the time we'll touch that. But that's not the only. We have in this moment two elements. We have the first one is the event is a specific event because we are working with vibration speed. But as well, we are talking about one moment in the time. So we have two elements. The third element is the risk. We add confidence intervals, as you see right there. So if you see the darker blue means that it's more probable to occur, and the lighter means less probable. So you have the three elements: a probability, you have a specific event, and one moment in the time to predict. And we transform that in reliability curve. So if you see the first plot is really easy to understand for us as engineers. But if it's not so clear, maybe just imagine maybe the CFO of a company trying to trying to understand that plot. But if you show him the last one, you will see something that is very simple. One means that your asset is reliable, will not fail. And if you see there's a point in the time that is falling down. And this is the key moment to make a plan. And we transform that we transform this curve in trying to make a plan based on this. So let's look the most important part of that plot. When reliability begins to fall. If you are using our platform, you can send to the CMMS a notification, a request to make a future work order to plan, for example, an inspection. So that's a first thing. But another important thing is just imagine the gray line that you have. Just imagine that the gray line is today, is this moment. And the red line is when is where the is when the reliability begins to fall. So we have the acceptable reliability remaining time. This remaining time is the time that you have to make a plan and execute it. So in this part, you have a very important indicator to work with it. So let's see a more holistic view from the company. You don't have just one model. You will have maybe more models, more degradation models. You have different assets, and you can mix them in one plot. And you can use it to make an assessment or make an evaluation of, for example, a priority list. Which asset you will prioritize. Another one is expected. How many expected failures will you have? And you can make with that a lot of plan and budgets about that. For example, retrofitting, overhauling, or condition-based maintenance. So this is the way how we make a reliability-based plan when you have a degradation models, very critical assets. So let's go to the other kind of assets. Too simple to sensorize, light bulbs, fans, things like that. What we did with that? So you only have times. It's the only data that you have. And you have to extract all the conclusions about this. The first thing, you can put all the data ordered, as you can see. And we can make a reliability curve with it. And after that, we can fit a model. And when we introduce, we extract two remarkable points. We called M and R2M. M is the median. It's a statistical median. Why is important? Median is the extreme limit in maintenance. Because in the moment of the median, you have the same probability that your asset work or not work. And after that, the probability of not work is higher than your asset work. So that's the limit value that you have. So you have the median. And if you make a very simple calculation, just take that 400 and add a half, and you have 615. When you see the reliability in that point, you have the R2M. In this case, it's a 10%. And you can make a very important conclusion about that. Just let me show you right here. This is a screen of Predictive. You can see a screenshot. And you have the endpoint. You have the endpoint right here. You have the endpoint right here and R2M right here. The reliability process is very different because you have the y-axis, you have a logarithm scale. So that's because you see different, but it's the same curve. Okay, and you see a line right there. You see a line about, there's a line about here, the 35%. We called accidental failure line. That corresponds to accidental failure when you have, in Weibull, when you have a beta equal to 1, that's the accidental failure right here. If your R2M are behind the accidental failure line, you have a wear out failure. If R2M is over the line, you will have infant mortality in that case. Of course, if you have over the line, just on the line, you will have an accidental failure. And that takes you to a very different conclusions about maintenance. Usually, when you have usually when you have, you are making a maintenance plan, the first question is, how each I have to make preventive maintenance? And that's not the first question. The first question is, should be, have I to make a preventive maintenance plan? For example, if you have an accidental failure, maybe it's not the best strategy to make. It's not the best. Usually when you have an accidental failure, it simply means that the failure can occur in any moment of time. You don't have a specific time when the failure will occur. So that's a huge problem. So the recommendation is just look for the primal cause of the failure. That's the way. So that's very important to make this kind of conclusion about the strategy, the reliability curve. You can see right here another, for example, we can extract operating periods, safe operation, start of degradation, on end of useful life. You can customize what means, for example, safe operation. You can define that safe operation is more than, greater than 90% of reliability, could be. And you can, as you see right here, is very clear how to detect if you have a wear-out failure, an accidental failure, or infant mortality. You can see that is because accidental failure is on a straight line. You can see right here. And you can see a curve, the curve in infant mortality and the wear-out is another curve, is very different from the other. That implies that it's easy to identify how to identify any specific behavior and how to make a strategy with it. Okay, but we can go further. If you have reliability, you can see another very important indicator as failure rate and Mtbf. Usually in the industry, Mtbf is simply an indicator. You take all your past information, make some simple calculations, and you finally have the Mtbf. But the problem is Mtbf is not constant. It's variable over the time. So you have different Mtbf when your asset is getting older. And we know that. That's the reason because when we talk about failure rate or Mtbf, we have a plot, not just a value. The third one is probability density function. That sounds super fancy, but is a very good plot, for example, for supplier selection. Just imagine that you want to know what is your best supplier, and you can compare one curve like this with another supplier. So you can make the difference. And when you see the difference, maybe you can see that MTTF, that is the maximum point of that plot, we'll see maybe one is greater than the other. And that tells you that there's one supplier that is giving you a better quality product. So you can make a quantitative evaluation about how to apply it to the day-to-day strategy. We have another, is we can make a calculation of accumulated failures. It's just based in the same models, just the same model. And you can, you have, if you can see right here, you can see one curve right here in colors, and you have a very thin straight line right here. We call minimum maintenance and maximum maintenance. Minimum maintenance means that what happened if when your asset failed, you repair it, and after you repair it, your asset remains in the same state than before the failure occurred. So in that point, you will have you have this one, this curve. This is minimum maintenance. And maximum maintenance is when you make a total replace of the part by a new one. And that one is this one, is the lower one. So in that case, you have two extreme realities. But in the real life, nothing is a minimum maintenance or a maximum maintenance. Maybe you are in the middle. So the central part of the plot, this central part, in some part of that, you have your real world. And you can make some calculations to know how many spare parts will you need for the next year, for example. So that's very important. And my favorite plot is that one, maintenance cycle optimization. We make a model when we add the probability of incur in cost of corrective maintenance and the probability to incur in preventive maintenance, and add those two. So you have a maintenance cycle operation. The y-axis is maintenance cost per year, and the x-axis is the how long is the maintenance period. So what you are seeing right here is you have an optimal part of the curve with minimum cost. What happens if you don't do any maintenance at all? You will have a very high cost right here. You will see it right there. But imagine that you want to make a maintenance maybe once per week. So you will be in that part, over maintenance, right here. So there's a part that you can find a minimum, an optimal cost of your maintenance, and it's right here in this part, and you can make a calculation when will be optimal. So that's we are doing in Predicto with that. So that's a lot of information that is really good, but how to build a maintenance plan with it? First, we have reliability, and we can, from reliability, obtain those 4 plots. But each plot answers one different question. In the first one, we talk about reliability behavior. So, and we talk about, we are talking about behavior itself, infant mortality, accidental failure, or wear-out failure. In the second one, we talk about risk evaluation. We can detect Mtbf, for example. In the third one, we have inventory estimation. And in the fourth, optimal cost and frequencies. Look, if you have inventories, you have frequencies of maintenance, and you have a very clear strategy, that makes you a reliability maintenance plan and budget. So let's put together both models, okay? The degradation and reliability models. If you have those two, you will have you have models based on reliability plot. And reliability plot, you can mix one reliability plot with another because are probabilities. What's the problem today? Today you are trying many times using artificial intelligence or machine learning or any other, trying to mix temperatures with pressures. of the same thing. And that's not clear, it's not easy to understand. Many times you want to take any system, machine learning or any other, to open the black box, look inside and try to understand if there's a good system or a mediocre or bad system. You don't know that. The problem is when you open up an artificial intelligence matrix, for example, inside, nobody understands what is happening inside. That's absolutely obscure. And we are trying to make a very a white box. That's all that you see here are probabilistic models, statistical distributions. So if you want, or the desire is, if you want to say that you don't trust in that system or the data, you can do it because you understand it. So we think that's the main value, to make decisions, to calculate the risk, to make a plan, to make a budget, and to trust it. So that's what we are doing in Predictive, and that's the way that we are trying to change the way that the maintenance is done. So thank you for your assistance. So is there any questions about that?
The question is it a statistical behavior of the reliability that you have?
That
the
depends.
First question.
Okay, that depends. The things that I don't show you here, but it's usually the way that we conceive all the business or the way that we make machine learning is that there's someone that makes the machine learning, no? And you use it. In this case, you can make the machine learning by yourself. So if you want your model will be a static, you can do it in that way. But you can recalculate the model as you have a new data. You can make new calculations. You can make filters, for example. Just imagine that you don't like all the data. And a retrofitting, an overhauling, that makes that is not the same asset anymore. It's a different asset. So you can tell to the system, I don't want the old ones, the old data, just the new one, after the overhauling or after the retrofitting. So, and you can make a new model with that information. So just imagine our solution as a specialized calculator, not a model that you put in some place in the cloud. It's like a calculator, an advanced calculator about reliability. It's just that all.
Yes, I am. I know that's the most important point in the issue of calculation of reliability is the dynamic calculation of the reliability, because that is a huge challenge. So if you are using machine learning to calculate the reliability value dynamically, we have a problem. The problem is that we use a machine learning. We do not know exactly the behavior, the decision of machine learning. And at the end of the day, we have a value of the reliability, which we use. Actually, we are not able to use it, because if we are producing a machine, it must be accepted by the government, you know. So we have some governments that they look after the documents, they look at and they say, okay, you are able to use this machine, otherwise it's not allowed. So you must show the exactly that your reliability calculation has worked exactly. Usually at this time, we use the statistical value based on empirical data that we have. But in the case of dynamic calculation of the reliability, we do not have the empirical data. We use some information that we have, we make a decision, and now we are at the point that we are not able to evaluate the decision. That's from my point of view, a very critical point, because we make a decision based on a decision which is not evaluated. That's, I think, is a critical point.
I understand you completely. It's a very huge point when we talk about reliability, and you must be transparent with the way that you make the calculation of reliability. The traditional machine learning. I don't know how to how to say that. Traditional machine learning is really weird. But when we are talking about stochastic processes, first is a way you can make a demonstration. You can demonstrate statistically if it's working or not, because you have confidence intervals. That's not the way that usually you use in machine learning, that you have training data and test data. What happened in the real world is not like your test data. Yeah, the behavior will be really different. Maybe it's telling you that the test runs really well, but it's not working in the reality. That's one of the problems. But in our system, it's transparent. The first thing is when you have a stochastic process, you're assuming that you have a statistical distribution through the time. So you can measure not only what will happen, as well the probability of that will happen in some point of the future. So we can put all the methodology on the light. For example, if there is a government requirement, we can do that, because we don't invent nothing. That's nothing new. The stochastic processes are discovered in the 70s, the past millennium. No, it's not the artificial intelligence that we are using right now. And we are talking about statistical distributions as reliability models. We are talking about well-known distribution as Weibull, for example. It's just so easy. We are not coming here to show you an strange technology. It's a proven technology that you can show to people. For example, risk an insurer, for example. That's the way that the insurers make their calculations to make a calculation about the risk, how cost you an asset insurance policy. We are making similar calculations, so we are compatible with the standards in the market. So I think there will be not a problem about. We are really transparent about how we make all the things. Our objective is not to make many things or many complicated things. Is make it easy. Not only easy to calculate, it's easy to understand deeply. We have a mantra in Predictive. It's simple to use and deep to dive. That is that one. And we hope we are achieving that with this platform. Thank you for your question.
Hello, Juan Tocayo.
Tocayo.
Name and last name. I'm Juan Villegas too.
Juan Villegas. Nice to meet you.
Nice to meet you. Well, I have a lot of questions, but first of all, how do you deal with the failure modes of a machine?
Really good question. Okay, this is another part that I didn't show you because of the time, but it's really important that when you make a model, that you as a user of the platform, you can select the data that you want to build the model. You pay attention to the failure modes. That's a really good question. Yeah. Anyone, you can mix everything if you want. Okay, you can do that. But that's not recommended, because usually if you have, for example, if you have a failure and you have, I don't know, maybe you have 98% of the data of one failure mode and 2% of the other failure mode. The second failure mode will be hidden behind the first one. That's the problem. So you have to make a differentiation between failure mode. That's really important when you build a model inside our platform, and you can do that. You can select. We can. So we have the failure mode concept inside the tree data structure of the assets. The failure mode is like the leaf of the tree.
Because an asset doesn't fail per se the full asset. It fails in a specific failure mode. A bolt gets broken, a sensor breaks, and then the whole asset fails. But a motor doesn't fail. It fails the fan or one bolt or the case or something like that.
Yeah, but you have another problem if you go to that strategy to put some failure mode to everything. Yes, when you have 100 data, for example, what happens if you have 100 failure modes and have 100 data? You will have, on average, 1 data per failure mode, and you can do that any model at all. So you should be careful what means a failure mode, and if one failure mode is comparable with another, and you can mix some data to get enough information to build a model.
Okay. Well, and another question, last one, if anyone doesn't have any more questions. The thing is that I formerly worked as a reliability engineer, and the company I worked for, it was fully corrective maintenance until I got there because it was fully correct.
That sounds rare.
Yeah, it was a mess. It was a real mess.
Yeah.
The thing that happened there is that we first tried that approach as an asset-based maintenance approach. So we made a maintenance plan based on each one of the assets, each one of the machines. What happened? When you tackle one machine, then the other one fails. Then you go tackle and it becomes another corrective maintenance approach. What we did is we changed to a component-based approach. So we did all the failure modes and effect analysis for all the machines, and we start doing the maintenance plans based on the component level. So instead of look at it were word drawing machines. So the length of each machine was the length of this room. So you couldn't tackle a machine in one day, and the machine couldn't stop. So what we did is, okay, first day you clean this sensor, then the next day you apply some torque to this bolt and something like that. And the question that I'm having is, haven't you tried maybe, instead of predicting what is the time of failure of the whole asset, maybe classify each failure mode? It's also a machine learning problem, you know?
Yeah. But we are trying to solve different questions. There's one. The question that you are asking is about let me call it the specialist point of view. Okay, you are a specialist and you are in front of the machine, and you want to make a easy diagnostic of what to do right now. Okay, that's one way to watch it. The way that Predictive watch maintenance is in the long term.
Yeah.
Okay.
Yeah.
Okay. But you can anyway you can answer both of the questions. But the main question that we want to answer is how to plan. What's the best way to plan? And let me make one recommendation about what you are talking about the case of your company. There's a very old tool, a statistical tool, is Weibo. And in Weibull, you have the shape parameter, if you remember. With the shape parameter, you have infant failures, accidental failures, and viral failures. Yeah. Many times, the problem is the first question that you make when you are trying to plan maintenance. And the first question that you make is how long take or what will be the optimal maintenance between one preventive maintenance and the another, the maintenance cycle. And the first question that you should ask is have I to make a preventive maintenance? Maybe that's the case of infant mortality. Just imagine that one asset, one machinery, when you touch the machine that is so complex, there's more probability to failure in the near future than if you don't touch it. Yeah. Imagine that's very typical. Imagine a bad quality of maintenance, bad quality of a spare part, a very complex equipment to maintain. So in that case, the answer is the optimal strategy is to you put it in front of the machine and you say, if I touch the machine, I have to make an inspection until the probability of failure goes down. Maybe I call as a protection period, okay? Yeah. A safe period. And you make an inspection right there. And indeed, in that moment, when the probability is is very low, you can let the asset run as normal operation.
Maybe I didn't expose it correctly, but the question is not how long does it pass between one maintenance and the other? Mm-hmm. Is as you said, okay, I'm in front of the machine and I need to inspect the machine. What to inspect? Okay. What part of the machine should I inspect? Because those are the failure modes.
Yeah.
The machine has
in our
million.
way to make the things, okay, to make a, you are talking about a classification problem.
Exactly.
Right.
Exactly.
Yeah,
that is like
I can understand that.
You can predict which part of the machine is going to fail.
But it's easy with that. It's just you have many reliability curves, and you see you put in the today point, okay, what's the order from lower reliability to higher reliability. That's your priorities. The lower reliability curve means that you have to make maintenance right now. Yeah. That's the way that we answer that question.
Okay. Well, thank you.
So thank you for the presentation. My name is Bernardena Mano. I'm a research fellow in machine learning in Cranfield University. My question is toward the uncertainty that you talk about. So I believe that there is uncertainty in the models. There are also uncertainty in the data that we have, and there are also uncertainty in the way that we understand or the guys that are doing the machine learning or understood what the data was about. So in your experience, did you have to tackle and combine data uncertainty with model uncertainty? Mm-hmm. And also, how did you handle the case that you talk about the imbalanced data set, where you have high number of one class but a low number of the other one? Do you have any suggestion for people that are facing the same situation?
Okay, the problem of the unbalanced data is really common in maintenance, because by definition, a failure is a rare event. So you have many information of the normal operation and very little of the failure. So that's a real and typical problem in maintenance when you try to make a prediction or use machine learning. The way that we do that is we try to extract just the information that is around the failure, not the normal operation. The normal operation is not really interesting for us. We are trying to catch the failures, right? So and when you take the information in that way, the information is naturally balanced because you only have the failures. Well, I understand that because when you work with machine learning, the first thing what you try to do is to put all the data inside it. You can think that more information is better, and not maybe that's not the case. This is not a good case. Usually, the best thing that you can do is that you have a machine learning system expert in identify normal operation. And that's the big problem. The way that we are doing is just working with the information around the failure. And I think that we practically discard the normal operation. We are only interested about normal operations. How long is between one failure and another? What's how long is the time? Is that just the way that we are trying to do the things?
Now we will have a presentation from Sergio Obando with respect to which is come from MathWorks, and Maria Jose now is going to present him.
Thank you, Professor Giacomo. Sergio is an application engineering team lead at MathWorks, focusing on the areas of data science, mathematical modeling, and parallel computing. For more than 6 years, Sergio has worked with companies and universities in the United States and Latin America in the adoption of MATLAB and Simulink in projects related to data analytics and integration with production and cloud systems. Before joining MathWorks, Sergio received his PhD, MS, and BS in mechanical engineering from the University of Massachusetts, Lowell. During that time, he worked as a research assistant at the Structural Dynamics and Acoustic System Laboratory, specializing in modal analysis and vibrations. Sergio also holds an MS in Applied Mathematics from Worcester's Polytechnic Institute and BS in Mathematics from Worcester State College. I would like to welcome his conference, Predictive Maintenance Algorithms Development with MATLAB.
Thank you very much. First of all, I want to thank the organizers of this event for the invitation to come here and present, and I want to thank the audience for their attention, and also to my colleagues, David and Juan, who did a great presentation, and I think it sets the stage fairly well for some of the information that I want to share with you today. I wish I could be there in person, but in the meantime, if you have questions for those that are remote, please send them through the chat. And for those that are in person, feel free to, I guess, hold your questions until the end, and I'll leave some space to answer those questions at the end. All the slides, all the code and things that I'm going to do today will be shared with everybody. So don't worry if you miss, a line of code or anything like that. Again, you will have all this material for reference. So what is the objective with the talk today? So again, the title is Predictive Maintenance Algorithm Development with MATLAB. And my goal here is to show you, give you a glimpse of the different techniques and technologies that create and deploy the models and algorithms that run in many of the smart devices that you may be using today. And I think the way that I'm going to connect this with the aspect of retrofitting is I'm going to show you a little bit how you can enhance or create synthetic data by using models, which is a good way, and I think David referenced this, to perhaps bypass some of the challenges of older machinery that you may not have any available data to create a model for predictions. So a brief agenda. I'll start, giving some concepts about predictive maintenance. I won't spend a whole lot of time here because I think the previous speakers have done a great job on this area. So I'm just going to throw in some terminology, and make sure that we're at the same pace. And then I'll enter into a couple of more practical examples. In particular, I'm going to show you how to create an algorithm for anomaly detection in the case that you do have data from your assets. And then on the second example, I'm going to show you how you can generate failure data from models and then predict what is the remaining useful life for those assets. Again, part of what we want to learn through predictive maintenance is, what is the useful life, or what is the maintenance cycle that I want to have for my assets. And while the end goal is something like this dashboard where I can monitor and see what is happening, the reality is that there are a lot of things that need to happen before I'm ready to do that. I need to have assets that can transfer and transmit data. I have to be connecting to that data. And then once I have that data, I have to make some kind of use of it, right? And this may require pre-processing of the data, selecting the appropriate algorithm, and then tie this to the predictive aspect, meaning can my data tell me help me make a business decision based on my available information. So some of the examples I will see today is, well, how do we actually get to that model? And what you're seeing on your screen is what could be a HMI or a dashboard for an operator. And it's just giving me a high level view of what is happening with my machines. So every here from 1 through 10, you're seeing different pumps. And what is being predicted here is how many cycles or how many days until I need to perform maintenance on it, right? So we want to predict that. And behind the scenes, what you see, some of the machines do need maintenance. And again, this can help an operator assess and prioritize those machines that maybe may not be working correctly. And again, when we say failure, I want to clarify, failure is not that the machine explodes or something like that. It just is reaching an undesired performance, or something that I'm measuring is not doing what it needs to do. Now, how do we arrive at a model like this? I will show you later on how we can build models and create synthetic data that can help me not only simulate types of failures that perhaps I won't be able to encounter easily in practice. It could be a good way to manage kind of the limitations of having one-sided data. And I think Juan answered this question from somebody in the audience, right? Like, what happens if you have too much data leaning towards normal operation and not enough failure data? So this can also be a technique that is available for something like that. We'll come back to those examples. Like I said, I just wanted to give you a quick glimpse of where we are heading with this presentation. Now, why perform predictive maintenance? Again, I think the monetary aspect of it is fairly clear, right? Many companies want to save money, right? Assets are expensive. Keeping them out of operation is expensive, but there's also the human cost, right? Failure for many machines can be dangerous. In the case that you're seeing here on your screen, it may mean that the asset may kill somebody, right? So these are things that can happen. So for many assets, taking them off operation is fairly difficult. So what you're seeing on your screen is a wind turbine blade. When I was a graduate student, we actually used to do structural testing on wind turbine blades. So we used to test 50-meter blades. And again, these are really massive blades. And for you to go to test them and check the turbine blade in operation, you have to take them offline. You have to get an operator in a crane. And it's a very complicated and costly process. Now, there's another aspect of maintenance that perhaps is not seen here. And again, there's a really big business opportunity for a lot of companies to provide predictive maintenance services, both to their own clients and to internal clients. Something that you may be seeing already is like your refrigerator or your dryer or your washer machine has some kind of maintenance device that can, emit a sound or give you a code. And with that code, you can call the company and tell them, what is happening with my machine? Should I service it? So there's a big business opportunity on the other side of the spectrum, where a lot of industries are looking to carry out predictive maintenance. So once again, I'm not going to go too much into the detail here. I think both David and Juan covered this really well. So we have 3 types of maintenance, right? Reactive, like changing something when it breaks, the battery dies, so I change it. Schedule, like changing the oil every number of kilometers from your car. And then predictive, when, yeah, I want to know what is the ideal or the optimal cycle or number of cycles to perform maintenance. So I want to give you some quick examples of customers that have actually carried out predictive maintenance approaches with our tools. So I want to give you a couple of quick examples of, again, customers that have implemented this kind of algorithms and that have been successful doing so. And again, I think the problem that you saw and that was mentioned in some of the other presentations is different industries are at different stages of this whole AI and Industry 4.0 mega trend, right? So some industries have very old assets, some industries have newer assets, some industries can afford to buy new assets and just discard the old ones. So there's always kind of a mix of things when you see this. On the left side, you see somebody like Baker Hughes, who was able to implement a monitoring system for their pumps used in the extraction of oil. And on the opposite end of the spectrum, we also see algorithms that are used to help operators potentially identify operation of their machines that are coming out of a desired range of operation. So what does a predictive maintenance algorithm do, right? So it's going to help me make a decision based on a given available data. And this was mentioned, again, this may be very large data sets for some companies. There are some industries that have been collecting data for ages, 20, 30 years of history. So this may involve big data problems as well as machine learning algorithms. And we typically will ask ourselves 3 types of questions here. Is my machine working normally? So this is what we refer to anomaly detection. Why is my machine behaving abnormally? This is more about condition of the machine. And then how much longer do I have, can I run this machine before it fails? And this is, again, something called remaining useful life, or RUL. And these are typically the type of questions that we want to answer with this available data. Now, how do I actually model or use or create one of those algorithms? Again, there's a whole range of things that you can do and a whole lot of combinations of these techniques that you can use. On the right side, you have data-driven approaches. On the opposite side, you have something like first principles, right? Maybe you can model the combustion engine. Maybe you can model the bearings and the degradation, or you can do something in between. Now, what do we actually do when we want to build these algorithms? So I really enjoyed the prior presentation, right? Because we saw a glimpse of all the different techniques that can be used, right? So from the statistical side to the machine learning side. But regardless of which of these techniques you pick, at some point you're going to have to acquire data or generate some data. You have to pre-process it, and you have to find what are called condition indicators. In some occasions, that may just be the raw data, right? So you have a temperature or an acceleration sensor. That may give you a sense of what the machine is doing, right? The operator may know that this pump can only run at a given temperature range, and that may help you gauge the current state of the machine. But it may also be more complex things, right? You may have to calculate spectral values. You may have to calculate averages, standard deviations, and all of those can serve as an indicator of what is happening within your asset. Now, the fact that we are using machine learning for many of those of this type of problems, again, is because we've seen the adaptability, the power of all of these techniques. And I'll talk a little bit about, what do I mean by machine learning, because there's a little bit of terminology here. But one thing to keep in mind is that this tends to be a fairly iterative process. You may need to reassess the quality of your data. You may need to reassess the type of model that you use. And if you find, for instance, that you don't have sufficient data, you may also need to reassess whether you have to take some time and collect additional data. At the end, what we want to get, or where we want to get, is to deploy and integrate these models into our production environment. And obviously, this is not a static model. I think we also heard a question from the audience, right? Some of these models need to be updated, need to be reassessed. And obviously, there are some challenges with that. But overall, we need to know that this is not a static thing that you do once and then move on. Now, why is machine learning coming into play for many of these type of problems? Again, the whole idea behind machine learning is, that these algorithms or these techniques help or create models that learn from data without actually programming them to, right? You don't have to write all the logic, or find an equation per se. Many of these techniques just learn from available data and are able to make predictions fairly accurately. There are many flavors of this as well. For instance, unsupervised learning, where you don't have any labeled data. So this is just more about finding trends within the existing data. This may come in play, for instance, for anomaly detection, right? I just have vibration data, and I want to know if something is off compared to all the other data that I have, right? I don't have a particular label to it. I haven't said, well, the machine was operating normally or abnormally, but I want to find trends or some kind of underlying behavior within the data. Supervised learning, again, this is the more what typically would come to mind. And this is just input, output, have a kind of a black box in the middle, and I'm trying to make predictions, right? So I fit some sensor data, and the prediction is I have X or Y number type of failure, for instance. And again, another set of techniques that also may come in play are things like deep learning, which is just a more specialized type of machine learning algorithm. The focus for today, I'm mostly going to be talking about unsupervised learning for the first example, which relates to anomaly detection. But when you do receive the code and everything, we do have additional examples there that show you how to carry out a supervised learning approach, as well as a deep learning approach for the data set that I'm going to be working with. So what do one of those models actually look in operation? So some of the things that may happen is that you are putting the device on board the asset, and you carry out kind of this process that I described, right? Analyze the data, find a model, compile it, and integrate it. And this is what Safran did. This is one of our virtual conference presentations from 2015, where they were implementing these techniques for a jet engine. So the example that I have today is a fairly well-known data set. Is 100 jet engines, and the data itself actually contains failure. So they have run to failure data for this 100 engines. But what we want to do is, let's assume that we have some historical data about these devices. Can we find anomalies in this data, right? Can we find where is it that the engine started behaving or going abnormally? There are some obvious sensors that are collected, which are the ones that you see here, things like the fan, pressure, high pressure chamber, and so on. So again, the first example is really about conditioning monitoring, or in a way, anomaly detection, where we want to find ranges where we say that the engine was operating normally, and then be able to assess that or help an operator assess that. Now, I can't really see the audience, but if somebody can help me gauge how many people have experience with MATLAB, I just want to know, how in detail do I have to go, or if I kind of have to give you a little bit of a sense of what the environment looks like. Can can we just take a quick poll? How many people have seen or used MATLAB in the past? I'll take a quick pause here. And if somebody from the organizers can let me know how many people raised their hand. Okay, so Bert, online, there's at least 1 or 2 people that have experience. How about in the room? Okay, this might be very difficult to do remote. All right, so for those that have never seen MATLAB, MATLAB is an environment that has an underlying programming language that is used for algorithm development, it's used for mathematical modeling and simulation of systems. So there are many libraries that we call toolboxes that align with different areas of science and engineering. So what I want to show you today is related to our predictive maintenance products. And I just want to show you a quick example. So I'm going to use an unsupervised technique to find anomalies in the data. And I've mentioned this is some engine data. So let me give you a quick glimpse of that, what that data actually looks like. So what I have are 100 Excel sheets. Each of those Excel files corresponds to one of the engines, and I have 100 of those. For each of the engines, I have the engine number, in this case 1. I have the different sensors, which in this case I have 14. And I have a time variable, which is referencing the flight cycle that corresponds to when the sensors were measured. All right, so the first thing that I want to do, and again, if you're not familiar with the environment, it is fairly easy to learn. And I'm using this this live script environment, which is a way for me to execute and comment or document my code. So when you receive this, again, there'll be kind of the context of what we're doing today. And again, we have 100 aircraft engines. Maintenance is done after 125 cycles. So we're going to look at those 125 cycles for all 100 engines. The first thing that I'm going to do is I'm going to load my data. So I'm using this function called read table to read the file for the first engine. And as you can see, this has just brought the information into the MATLAB environment. I may be interested in just taking a quick assessment of what is in here and potentially visualize some of this data, right? I need to be able to see, is there some kind of behavior that I can see just from visualizing? So let's do that. Let's visualize a couple of the engines and a couple of the sensors for those engines. And again, if you're not familiar with the asset, this may be kind of hard to interpret, but really many of the predictive maintenance approaches rely on the collaboration of the analyst or the engineer creating the algorithm with the maintenance department or the experts in the area. So sometimes you can call this like human in the loop, right? So one of the maintenance personnel may know, oh yeah, this is really not that great. I would think that around here, I would probably start thinking of doing maintenance for this engine. There are more formal ways to do this, although don't be surprised if this visual inspection is done in many industries. There's an expert that has a calibrated eye, and they're the ones that know when things need maintenance. But you can more formally do this using things like control charts. And you may say, well, after I have 3 or 4 points that go above the upper or lower controls, I may start deciding to perform maintenance. Now, part of the idea behind predictive maintenance is that you have to manage very large collections of data. So this is really something that has made my life a lot easier when I'm doing this kind of analysis. It's something called a data store. And what I'm going to use that for is to tell MATLAB that I have a collection of folders and data within those folders. And I want to use all those folders by reading or potentially analyzing all of those files. Something a little bit more advanced that I'm doing here, and again, I don't want to get too much into the weeds here, but I'm using something called a toll array, which is going to help me manage the fact that this data may not fit in the memory of my machine. So let's say you have 30, 40, 50 gigs of data, so a big data type problem, then you have to find some ways to either sample or subsample your data, or pick a smaller population from the available data set. Now, with this kind of techniques, I can just let MATLAB do everything, and I don't have to basically adjust my analysis to the fact that the data may not fit in memory. The way we do that is by creating this type of tables that don't read the data until they need to. So if you see I have M rows, the fact that it's M is because we don't know, we haven't read the data. We just know that we have a lot of data, but when I need to read it, I can do that. We just work with this type of tables like we do with any other variable. All right, so I'm going to take 5,000 samples, and I'm going to show you kind of a big picture of what all of those 5,000 samples look like for 100 of the engines. And again, this starts showing you a little bit of the difficulty in interpreting data once you start getting large amounts of data. Now I no longer have just one trace, I have 100 traces, and those traces also vary in range. They vary in, kind of the values that they vary from. So these are some considerations as you start doing this type of analysis, that first of all, you may need to standardize this data, right? You may have to normalize it, and you may have to be careful about what kind of pre-processing you do to the data to ensure that your algorithm gets the best data that it can. So that's the first thing that I'm actually going to do. I'm going to normalize the data. So I'm going to put all the signals from the range -1 to 1, right? And again, this is just to help my algorithm work more reliably. Now, the technique that I'm going to use for the anomaly detection is something fairly well established, fairly well known, is something called principal component analysis, right? And for principal component analysis, basically is trying to find a linear combination of all of your predictors, and you find the directions in which those predictions, the direction in which that combination of predictors is the best fit, let's say, where the variability is smaller. So let me just run this algorithm here, which is called PCA. And what you're seeing here is just MATLAB parsing through this very large collection of data, and is doing it in pieces or in chunks to help me be able to read or analyze all the data, because it doesn't fit in memory. Now, once I obtain those principal components, the idea for principal component analysis is that you can condense a very large dimensional space into a smaller number of dimensions. So I can take all of these 14 predictors and potentially look at 1 or 2 of them. So if I take one principal component, I can explain about 75% of all my data. If I take 2 principal components, I'm getting somewhere around 89 or 90% of my data. So what does that mean? That if I look at principal component 1 and 2, if I look at the plane formed by those 2 principal components, the amount of points that fall outside of that plane is fairly small, right? We're capturing about 90% of the variance of our data just with that, with those 2 principal components. Now, if you're interested in using different anomaly detection techniques, I just take a quick detour here. Let's just look at anomaly in the documentation, and there's a lot more examples here. For instance, unsupervised anomaly detection, and there's a couple of techniques that are shown here, like Support vector machines could be one, something called isolation forest, which is another great way to find outliers in a data set. And many of these examples, again, will give you a full set of code that you can just run and modify and adjust to your own data set. For predictive maintenance in particular, there is also a few application examples for different type of machinery. So in this case, we're using vibration data, and we use, I believe they use an SVM to detect anomalies. All right, now going back to PCA, what I will do here is I want to use principal component 1 and 2, and I want to look at all the data with the lens or by mapping it to these two principal components. So what you have here is a scatter plot that also does binning, meaning that each of the squares that you see on your screen is representing a certain amount of data, or the density of the data around that, around those values of the principal components. So what does that tell me? That if I have this darker blue color, most of the data is kind of centered there. So this is probably the range where most of the engines are located. And then you have all of these additional values that fall outside. And I should have probably picked different colors. This is probably green, meaning it's functioning well. And all of this outside is probably where we may start seeing some deviation from normal functioning. So let's pick one engine and let's take a look at how those engines map to this new set of principal components. And this section here that I quickly browsed through, this is just a way to tell what is the contribution of each of my predictors to the first principal components. So it looks like most of them contribute about 20 to 30%. So there's a good amount of contribution for all of them. But this is just, again, a way for you to assess, which one is the more dominant predictor for your principal components. All right, so once again, I want to take a look at one of these engines, and I want to see in this new framework, which is principal component 1 and 2, where are the points where the engine starts and where the engine ends. And the reason why I want to do that is I want to know if these principal components can help me detect anomalies, right? Can help me find where my engines are falling outside of normal operation. All right, so a quick picture here. In blue are the first point, meaning cycle 0, the first measurement that I took in the history of that device. And then all the points in red, which are all this bigger area here, are points where the last measurement, so meaning after 100 cycles, mapping those sensors to those two principal components, this is where that value of those sensors ended up. Now, how does this map to creating a predictive maintenance algorithm, which is the goal of this whole spiel that I'm talking about? The way that this works is that if I'm able to determine what the proper ranges are for these principal components, this could be a condition indicator, which tells me that as long as my device is within this region, everything is okay. But as it starts moving away, then I have to take some kind of action. So let's talk to the personnel, to the maintenance department, and let's see if they can help us identify one of these problematic engines. And let's see if this technique could be helpful. So we know that there's 4 engines, engine 39, 57, 70, and 91 may need some maintenance. So let's see if this approach can be useful. So, well, the first points are around this huge cloud of points, and eventually it moves away, starts moving farther and farther away from nominal functioning. So even better, I'm going to show you a quick animation that kind of shows you how from the first cycle, the engine is moving farther and farther away from nominal functioning. So every data point, is the engine or the measurements of that engine at a later cycle. So it starts somewhere here around cycle 0. And after 100 cycles, this is where this linear combination of sensors ends up. All right, so it sounds like there's some promising outcome for implementing this kind of technique. So let's use the available information to create a set of ranges. And I know that this looks like a huge chunk of code, but it's basically just saying if this is larger than a given value or smaller than a given value here, I'm going to say that everything is okay. Once it goes outside, it's an alert or warning. And then once it goes outside, yeah, this is really bad, right? This is, I really need to do maintenance now. This is, I need to schedule it within a couple cycles, and this is, everything is okay. All right, so let's see if implementing this kind of scenario would be actually useful. So we do have available data from when the actual engines fail. So we can use this existing data to help me corroborate whether the approach was correct. And what we find is that, well, if I include normal and warning conditions, I can capture about 99% of my assets. And when the devices were in a normal range, 89% of the time, we capture that correctly. Again, we just want to make sure that we have a way to corroborate, basically verify that the algorithm is correct. And as we have more available data, we can always extend that and validate or tune the algorithm further. All right, so I'm not going to go through the rest of the exercise here, but basically it's just taking additional data, running it, looking at the cycles after 125 and seeing if our algorithm properly capture that information. So how could we actually put this in operation? Well, one potential way is to say, I take all my 100 engines and I do maintenance on them. And that becomes my new route, my new cycle 0. Now I start implementing this technique, right? And I know all my assets have maintenance. And now in the second round, or in the second cycle of maintenance, I start pushing that that maintenance cycle by a few additional hours or days or whatever your cycle of maintenance is. And I use my algorithm to help me prioritize the devices that or the assets that I perform maintenance on. So I've pushed it by 10 more flights. So rather than having maintenance every 125 cycles or flights, I pushed it by 10. And then I only did maintenance in between for those assets where there was an alert by my algorithm. For the rest, I just waited until 135. Now in round 3, as you may imagine, I may be able to push this a little farther. And I'm just kind of tuning this anomaly detection to help me prioritize the assets that need the most immediate attention. So this is a stage adoption of an unsupervised anomaly detection technique to help me guide how often or after how much time I perform maintenance. So this actually was what this company Mondi did. And what you can see here is actually very similar to our example, which is an HMI for the operators. They are able to quickly gauge where in these 3 ranges the machine is working in, and again, prioritize maintenance based on that. All right, so I mentioned that I wanted to do 2 examples. So with the remainder of time, I want to start looking at well, what happens if I don't have sufficient data? Or what happens if potentially my device cannot be instrumented quite yet? So it may happen that I actually understand very well how the device works, or it's a fairly well-known device, and I can create a model. So you may have heard this expression of a digital twin, right? A digital model of my working asset. And I will use this digital model to help me guide and potentially make predictions. So this is a triplex reciprocating pump. And again, what we want to do is we want to simulate different types of failures that can occur with this device. So the failure or the types of failures are coded with this 8 different codes, and it's basically different combinations of these potential parts that tend to fail or require more maintenance. Once again, I'm relying on the experience of my personal or my maintenance department to help me guide how effective these predictive maintenance algorithms can be. So I have 3 parts that were identified to be the more prone to maintenance. And I use the combination of those, right? So 2 to the 3 is 8, and those are the 8 different fault codes that I can get. So what I'm going to do with those, with this is I want to give you a quick view of what the model looks like, and I want to give you a quick view of how to build a model based on that. So let me go back to MATLAB. And let's look at the pump maintenance example. All right, so let me once again show you this model of the pump that I showed you earlier. So this is what the actual pump model looks like. And what I'm using here is I'm using a platform from Simulink, which sits on top of the MATLAB environment. So Simulink is built to simulate dynamic systems, and it helps me tie physical modeling of multi-domain type problems and the mechanics or the dynamics that go behind the scenes. Now, let me just start running this model. And again, you already saw me do this earlier. I'm just going to run this pump under normal operating conditions and take a look at some variables of interest. So the 2 variables that I'm going to be simulating or keeping tabs of are things like the flow in and the flow out of the pump, as well as you can look at things like input pressures and so on, and input also flow to the pump. All right, so here is just the animation under normal conditions. And again, there are a lot of things that go behind the scenes to create this kind of model. So if you're curious kind of what goes behind the scenes, you can certainly take a look at each of the components and the different ways that this is being modeled. And I'll share some resources at the end of the presentation so you understand kind of how to build these models from scratch. We also have a webinar called Model-Based Design with MATLAB, with Simulink, which kind of walks you through the process of creating this type of models. All right, so let's look at the flow rates in and out. So we have flow in and flow out of the pump, and this is what is occurring under normal conditions. Now, I said this type of model, of digital model, can help me model certain types of failure. So what we did, we integrated different types of faults that I can just turn on or off. So I'm going to, for instance, say that in one of the seals or in one of the plungers here, this is going to be leaking, right? It's going to be letting certain amount of fluid out. And I'm going to say that there's also some kind of bearing wear right here on the rotating part of the shaft. All right, so I'm going to apply this. And I'm going to run my simulation one more time. All right, so this is again the physical or the physical view of what is being simulated at the time. And again, I'm just simulating a small fraction of time. So if you have very large models, if you have you know, a lot of components, there's certainly a lot of things that we can do to optimize and also scale these models using cloud resources and compute. All right, so now let's compare, or let's look at the flow, right? So if you don't remember exactly, but this looks very, very different to what we saw on the normal operation. And again, one thing that may not be immediately obvious is that it is very costly to get failure data. And it may be almost impossible to simulate or capture the data for some failure modes. So here, there's a way for me to create models and tune those models to be a good representation of the physical asset. Now, as a maintenance personnel or as an engineer, I can start looking at all of those simulations and see if there is really something different, right? So I can look at, let me look at the flow out of this. And let's look at the flow out on the normal conditions. So you can see that it's very different. And again, this is the type of data that I can now go to my machine learning model or my remaining useful life algorithm and use to make predictions. So let's do that exactly. So going back to the workflow, again, we have to acquire or create synthetic data. We pre-process that data. We identify condition indicators, and then we train the model. So the first thing that I'm going to do is I'm going to do some feature extraction. So I need to be able to feed feed features to my models. And luckily, I have this digital model. So I'm going to generate a huge sample of those histories or those signals. And then I'm going to create a predictors or condition indicators from those. So all I've done so far is I've loaded my data, but let me use something called the Feature Designer app. So what the Feature Designer app is going to help me do is interactively create or compute features. So let me just move this to the other screen. So the first thing that I'll do is I'm just going to pick my data set. I'm going to pick the sensor data that I measure or that I synthesize, which is flow and pressure. And I actually have the full code that is associated with each of those failures. In other words, I have my condition variable as part of this data set. I'm going to import. And I want to quickly show you what all that information looks like, because I have about 240 simulated runtime histories for all the simulations that I run. And here you just see a very large collection of all of those measurements. So what is the goal again within this feature designer is look at your data, start seeing or potentially uncovering some of the trends and create indicators out of that data. So for instance, I could take the flow and start generating features, and I may obviously need to do some pre-processing. So there is the ability to help you do the pre-processing directly from within the app. So I'm just want to point that out in case that you find that your data needs some pre-processing, which I can guarantee you it probably does. All right, so let's compute, for instance, some signal type features. So these are time domain features, typically what you would expect for values of interest, things like kurtosis, mean, standard deviation, and so on. So with just one click of a button, I can just select all of this and say apply. And what MATLAB is going to do is going to run through all of those 240 histories and is going to compute all of these features for you. Now, the next thing that you'll see here is a histogram. And what we're looking for in this histogram is, do any of these features that we've computed help me separate or distinguish between each of the faults that I'm trying to predict? So what we really want to see is potentially if we had 8 separate, for each fault, we have different values, and we don't want to see everything condensed into a single block, because it means that that predictor is not very powerful. So we can go through this process, and again, there are time domain features. If I'm interested in computing things like frequency type features, I can also compute the spectrum of those signals. And then with that spectrum, then I can compute frequency domain type type of features. And again, this may be for rotating machinery, many assets. That may be a very powerful predictor, as many of the presenters have also described. So shift in frequency of damping and so on is a very good indicator of a lot of failure types. So now with the spectrum, the last thing that I do, like I said, I can generate a spectral features. And then at the end, once I have a very large collection of features, I can rank those to know which of these features capture the variability of my data best. So for instance, here, it looks like for the flow rate, at least, the RMS tends to be of more importance based, in this case, of an ANOVA type of analysis. Now, what is the next step in that workflow that you saw in the slide? Once I have computed features, I can use those features and pass them to my algorithm. And if I'm using a machine learning type of technique, I could just feed that into my machine learning model. One thing that I want to point you to is this function right here, or this option right here, which helps me take all of this interactive process that I've done, so all the point and clicking that I've done so far, and it helps me create MATLAB code that takes care of all of that programmatically. Now, why would that be important? Because more likely than not, what I want to do is put this in some kind of automated or production type environment, where most likely I won't have the possibility to do point and clicking or anything like that. I want to be automated. So that's what we did with our code, and we use that to train. We generate the features, and then we use that to train a machine learning model. So that would be probably the last part that I'll do. I'll show you how to train a machine learning model, and then I'll pass to answer some questions and share some additional resources with you. All right, so I have all of these features that we've collected. And again, we use the diagnostic feature designer to help me generate 40, I believe 40 features or so. Yeah, 40 features that I can feed to my model. So once again, I'm going to use something called Classification Learner, which is, again, another interactive environment. It's an app that helps me train classification type machine learning models that can be used not only for predictive maintenance, but for any kind of analytics that you're working on. All right, so I'm going to load those features that we generated. So train features and labels. So here you have all of those features that we computed, and the thing that you're predicting, right? The response is this variable called fault code. All right, so obviously I need to validate whether my model is doing the right thing or not. So you can certainly generate or use different types of validation techniques. I'm going to just use a cross-validation and there are reasons why you may want to do that. I highly recommend we have something called machine learning on ramp, which I will show you at the end of the presentation. And this is if you want to learn more about machine learning and how to run those type of models. But what I will do here is I'm going to tell MATLAB to just train a bunch of those models for me, and then just tell me which one works best. And the way I would assess which one will work best is typically I will look at something like a confusion matrix to gauge or to see how the predictions are done in comparison to the original data. So a decision tree in this case gave me the best performance, which was really not that great, about 71%. And I can see here in the diagonal, these are the predictions that are done accurate, meaning when my model predicted that the failure type was that of code 11, it really was code 11. The ones or the things that are off diagonal are the ones that were misclassified. So for instance, it was really code 110, and it was predicted as class 0. Once I have this trained machine learning model, the next step is, again, I mentioned implementing this in production. So you can export the code or generate a compact version of the code that may be used in to generate code for the device where this is going to run. And I'll talk a little bit about this towards the end, although it will not be the focus of the presentation. All right, so for the last part, let me just come back to my my example. And we take those features, we train a model, and at least with just the first approach that we did, we get about 77% accurate model. There is an additional section of the code where we tune the hyperparameters and we do some additional tweaking until eventually we can bring that model up to about a 95% accuracy. All right. So there was one part that I did not cover in length, but is fairly important to predictive maintenance, and is this aspect of remaining useful life. So I just want to quickly give you a glimpse of what that looks like. And there are also, I believe, the two prior presentations showed us a little bit of the algorithms that go behind the scenes. So let me just make reference to those. So you may have things like similarity models. And this typically means that you have run to failure histories of the machines that you're trying to diagnose. And what you're doing is you're comparing those run histories to new machines or new data as it becomes available. Degradation models, so those are typically those where you know the range of operation of a condition variable, and you're using that range or that threshold to create or prescribe a range and fit a time series model and use that to make the assessment of the remaining useful life. And then the last one, which I believe my colleague Juan explained as well in a lot of detail, is survival type models, right? So it's using things like proportional hazard models, probability distributions, and this is typically using lifetime data of similar models. So I guess the difference here is think like, I have batteries and I know how many days that batteries have lasted historically, and I want to know if a new battery has what the durability is of a new battery in my batch or my production batch. So we have in our library and in our toolbox all of these types of algorithms. For this particular data set, we chose a degradation model because, again, we know a couple of things about this. We have known thresholds, and we can create or synthesize a condition indicator to train a model, a remaining useful life model. All right, so let me just quickly go through this. So I can train an exponential degradation model. So I take a look at a condition indicator for that particular pump, and then I can use that condition variable to train the model. As I do have historical data and non-thresholds, I can use that to update my model as the data comes in and seeing what the remaining useful life of the asset looks like. So I'm gonna let that run, and at the end, I'll show you what this animation looks like. Okay. So this will be the final results, which tells me that for the particular pump that we picked, there was about 5 hours left of operation. So let me run this again over here. For some reason was running in a different screen. My apologies. Here it is. So as we feed the data to this remaining useful life model, you can see that we are trying to find similar models or profiles based on other, and until we can narrow down to the current state of that device. Now, I know that I went fairly quickly over this, so I just want to point you to the section of the documentation where we cover this in a lot more detail. So if you go to the predictive maintenance toolbox, you are probably going to see some similarity to today's presentation, where we start discussing, data management, pre-processing, generating indicators, and then detecting and predictive faults. In this detect and predict faults, there's a section for remaining useful life, and you can just look at particular application examples. Or if you're interested in the different types of models that are available, then there's a good diagram here in an explanation of what each of those models is capable of, or how to best pick the right model for the right type of data. All right, so let me just go towards my concluding slides. Second here. All right, so again, we want to use the expertise of the equipment manufacturer, the equipment maintenance department, and we can use that to build model, inject failures, and synthesize new data. We can fine tune that model using sensor data and use that to get the most accurate model. So that was the last part of the of what we did based on the triplex pump. All right, so at the end, what you want to deliver, or what many people will deliver out of this model, is some kind of practical or deployed model. And that may take the form of a dashboard. It may take the form of some kind of alert system. And again, there are many ways in which this can be incorporated. Now, for our tools, we typically provide a large flexibility. You may decide that you want to generate PLC code directly from your algorithm to your control system. You may decide that you want to translate that to C or C++ to put it on an edge device, or you may create some kind of dashboard to be integrated in some kind of deployed or cloud system for operators to take a look at. Again, this is a high-level visualization of what we went through, and I just want to point you to some additional resources, and I'll conclude with that. So we have these things called deep learning on ramp, and I want to remind you, for many of the students that are in the room, your university most likely has a campus-wide license, which is the case of Universidad de los Andes. So you have access to all the tools that I showed today to work with. These on-ramps are free. They don't require any kind of licensing, and you can take them at any point online. I'd like to point you again to some additional self-paced courses as well as our predictive maintenance website. And if you speak Spanish, we do have a new channel in YouTube that covers this seminar called Predictive Maintenance with MATLAB. We also have this Tech Talks, which is a series or short videos. So I highly encourage you to take a look at those. And again, if you have any questions, if you need assistance in your projects, please let us know. We do have training, consulting, and technical support that can help you in any of your long-term goals related to predictive maintenance. I want to thank everybody for their time, and I know that I may have a minute or two for questions. But once again, thank you everybody for your time, and I'm happy to chat and discuss any additional questions that you have. Thank you.
Yeah, so I repeat my question. So first, thank you for the presentation. It was really interesting. So I have 3 questions, and I'll be really quick with them. The first one is regarding the first example you mentioned about developing this unsupervised learning algorithm. How can we implement this unsupervised learning algorithm in online prediction? Because eventually there is no model to predict in an online scenario.
Yeah, so the challenge with unsupervised, you said it is very difficult for online systems. And I think a stage approach, very similar to what was shown, may work well. There's a lot of research in machine learning about different unsupervised approaches, and some of them seem very promising. But in many occasions, I see fault and anomaly detection as a starting point for many companies that are not quite ready to get to a remaining useful life type of model. So the idea is you start with this type of models to gain some insight into your data. And as you collect more data and gain that insight, eventually you may arrive to a point where you can do a supervised type approach. But yeah, it is fairly complex for some of the online systems that you're referring.
Okay, thank you. Regarding the simulation data which you generated, I didn't get the part where how did you model the degradation of the part? Because in a time series process, how do you model the degradation? How can you predict that, okay, after some time the part is getting degraded?
So that's a good question. So some of them may vary depending on the type of physics that you're trying to use, but for this particular simulate model, for instance, a valve being clogged, maybe an attenuation on the input electric signal, or it may be that you can look at the model and the physical component to the model and put some kind of barrier or some kind of ramp, for instance, to simulate the physical behavior that you're experiencing. It may be that for you to be able to actually assess what is happening, you may have to use real data to tune that digital model. But I mean, if we have more time, I can open the model and show you kind of the specific parts that that we use to kind of simulate those type of failures. And some of them may not be, let's say, perfect. Some of them may require some tuning. But the idea is that you can use these digital models to capture failures that may not be realizable in practice.
Yes, thank you. Exactly, that's the challenge also, because we don't have the data, and in many examples we don't have the data, and that's why we are going to these digital models. But then we need real data to make the digital model look better. I mean, perform better. So it's a bit tricky. So that's why I was curious to know how you model that.
Correct. So part of this, for instance, in the manifold, I may be able to put some of the failures, right? So if flow is going through a particular pipe, what I may do is put some kind of chamber, and that is going to simulate, for instance, that it's not working. Or a seal leak, some of the components, we actually have models that incorporate that into our libraries. So some of them, you just be able to select that type of situation. You may be able to just put a part into your valve and just take a little bit of fluid out and model an orifice, which is simulating the leak. But I know I understand where the question is coming from, and that's why I wanted to give you kind of two flavors of it. The first one, which is the ideal scenario where we have tons of data, you have failure data, and things are very easy. And then the one where you have a digital model that may not be perfect, but it may be a star, right? And as you start collecting more data with your real assets, this is where you could come in and really tune that model to be a good representation of the real asset. But yeah, typically this may be a stage approach, especially if the type of device that you are modeling is not well understood, kind of the physics, like some kind of oven, or the physics are too complicated. So it may be very hard to generate something like this for something like that.
Yeah. Yes, thank you. One last question was, how do you compare MATLAB with the open source softwares, which open source libraries that is available, especially in Python? I mean, what is the advantage or disadvantages of using MATLAB?
So that's a good question. It's a little bit philosophical, but at a large level, we see that many customers and engineers are using kind of a combination of tools to basically use the best tool for the right thing. In particular, in machine learning, we see a lot of open source being used to complement the analysis that you are doing potentially with MATLAB or with other tools. I think the benefit or the added value of a lot of commercial tools, and in this case in MATLAB, is validated tools that help you go through the complete workflow. I didn't show this too much, but the ability to generate code that goes directly to the device, a documentation and a support team that can help you implement and carry out this type of algorithms. And again, I don't think in many occasions it's an either or type question. Is you may be using our algorithms for one part of the process, but I find it hard, for instance, in the part of controls, in the part of signal processing. These are industries or these are applications where MATLAB is supremely dominant, for not saying the best. And there are areas where we really do appreciate people bringing in things, like we have a connection with TensorFlow to be able to bring deep learning models into the MATLAB environment. So we understand that customers and students need to learn and need to use all of this. So we are hoping to provide a very comprehensive set of tools that can help you solve real problems, but also integrate with existing solutions and existing languages and programming environments.
Okay, yes, thank you. You answered my question. Thanks a lot once again for the beautiful presentation. Thank you.
Thank you all for your time. And if there's anybody in the chat, I can keep answering questions through the chat as well. Thank you.
Thank you, Sergio. For our last conference of this graduate pre-workshop, Carlos Mortera and Daniel Garcia will talk about smart retrofitting solutions for Latin metalworking industry. Carlos graduated from Monterrey Institute of Technology with a BS in Computer System in Monterrey, Mexico, pursued master's degrees in Business Administration and Manufacturing Science from the same school. Mr. Mortera's experience in the industry includes working for Emerson Electric, where Carlos held several positions in industrial engineering, international trade, finance, HR, and materials in North America. He also worked at Cummins Inc., where he was responsible for various areas such as procurement, ET, operations, engineering, and general management for their business in Brazil and Mexico. Carlos' experience also includes working as VP administration for a sanitary ware company from Asia and managing a multinational company producing and marketing cooling towers in Americas. Carlos lived in Sao Paulo, Brazil for 4 years as general manager of the Brazilian division of Cummins Filtration and exhaust traveling extensively in South America. Carlos joined IMT in 22. He is fluent in 3 languages, has broad experience green fielding and broad fielding of small to large operations. Finally, Daniel García graduated with a mechatronics engineering degree from Technological University GAL, Escobedo, also complete a technical degree in electronics and automatization from the same university. He has diplomas in automation, artificial vision system, lean manufacturing, leadership, and certifications such as ISO Internal Auditor. His professional experience is brought through several turnkey projects and initiatives developed in Latin America, working as engineering manager at IMT, also international and domestic industries from Nova OMPI, SRL, and manufacturer of containers for the pharmaceutical industry, where he held positions as supervisor of maintenance electronics, GI Prolec, where he was responsible for the maintenance activities in the low voltage lines at Nemak, the largest independent manufacturer of automotive blocks in the world, where he worked as an intern and in the maintenance department. So go ahead, Carlos and Daniel.
Can you hear me all right? Good morning. Good. Well, thank you. I know that we are the last, presentation before lunch, so we're going to try to keep it dynamic and talk to you about, some of the initiatives that the industry around Latin America and as perceived by AMT and its membership. In order to do that, we're going to start with a presentation that explains to you what we do at AMT and what we've been doing for the last 120 years, all right? Not myself, of course, almost. It's only 119 for me, but still. So the name of the presentation is Smart Retrofitting in Manufacturing. The more we travel through Latin America, we see more and more, job shops and, tier 1 and big OEMs, which are thinking about how to really take advantage of the data which is available through there. And then that's what we're going to be presenting today. So please.
Manufacturing, the bedrock of the modern world. The Industrial Revolution gave us the mill, the lathe, the grinder. Small gestures that left large strokes. And through the decades, AMT members dreamt, built, pushed. Advancements came in waves, their spray lighting new horizons in the sunlight. And in the warmth left for others to feel, our members reached for possibilities that others could not see. Since 1902, AMT has seen it all because our members built it with the tools we gave them. Today, we embark upon the digital revolution, where manufacturing technology opens new doors to new realities and to solutions to questions we couldn't dream of. Today, we continue to shape the future of our industry by advancing new tools for a new age. The place where leadership, manufacturing, and technology come together in unity. AMT, Advancing Manufacturing Technology.
Explaining to you all some of the benefits and what is the actual state of the ecosystem in Latin America and the rest of the world as it relates to what we do through AMT. But quickly, what we do at AMT is basically we facilitate forums. We're always trying to promote the technology transfer and making sure that the end users of the technology are well versed on what is new. And that's where the interaction with some of the universities like Uniandes, Tec de Monterrey, and many more universities both in the United States and around the world help us promote the technology transfer and making sure that the platforms and the curricula and the whole syllabus which is presented to then the students is really reflective of what the industry is needing. We also have a lot of events that we produce. One of those is the largest manufacturing technology show that is presented in the Americas called IMTS. And then we support the growth of global business. We know that for every dollar invested in manufacturing technology, the wealth which is generated in those countries which are investing, or those entities which are investing, the wealth and the creation of wealth is about 3 times as high as that dollar or peso colombiano which is invested. Go ahead, Daniel. The range that we have includes, the whole realm of manufacturing technology, as we call it, from lubricants to machining to automation to additive manufacturing, industrial automation, assembly and test, and many more, software CAM, and a lot of the new platforms which are developed there. And it was just natural that we started thinking, and through our OEMs, started thinking about what is the effect of smart retrofitting, and what are some of the value propositions that the OEMs are now putting in place. All right, go ahead. So in order to just normalize for the benefit of the audience, how is the ecosystem in Latin America? I'm going to talk a little bit about what is the demand and why is it important for these economies, which are trying to grow and expand and create more wealth for the development of the citizenship. All right. First of all, this year is going to be one of the best years in consumption manufacturing technology worldwide. Even with some of the dynamics and the variables which are, the headwinds which are stopping the growth of the industry, we see that this is going to be a tremendous opportunity for growth in demand on manufacturing technology coming out of the pandemic. 15 out of the 18 manufacturing sectors, both in the United States and Europe, are growing, and are showing revenue improvement, and those are good news. Some of the new technologies which are being implemented, from electric cars and autonomous cars and mobility and a bunch of different things, are really pushing forward the research and development. Go ahead. This is the overview of the Latin American market. I'm responsible for the Latin American economies, which are industrial, and this is what we see happening over the next year. And so, in regards to growth and development, the more growth that there is, then the more consumption, manufacturing technology, and need for innovative solutions are taking place. So the key markets into this realm have to do with the 5 industrial economies which we monitor every year, which has to do with Mexico, Brazil, Colombia, of course, Argentina, and Costa Rica. Go ahead. That's what I show here. Why is this so important to AMT and its membership? Because, the manufacturing output, which is coming out of those 5 or 6 countries that I just reflected, it's close to $600 billion worth of manufacturing output. This is almost 1/3 of the total output of the United States, and it's almost like 1/4 of the total output of the Western Europe. So it's that important, the growth and the volume produced in Latin America. Go ahead. So consumption, as I explained, it's really important. This is just an overall consumption of the manufacturing technology realm for 2021. It reached $6.8 billion worth of consumption. This is not including automation. This is not including metrology. And so if you compound those 2 figures and then add the growth of the consumption, the use of adoption of manufacturing technology through the Americas, this is going to really get to about $10 billion. So that is the opportunity of the market, and that is the need and the outcry of the manufacturing community through Latin America, which is why we're here today. All right. So now we're going to talk about the adoption of technologies in Latin America. We in AMT, through our Vice President of Technology in our technology department, we're always measuring and monitoring what we call the transformative technologies. For us, transformative technologies are those which are going to really change the landscape of a job shop or a manufacturing facility in the next 10 to 15 years. And we identified 10 of those, and Daniel Garcia is going to talk to you about some of those things and the state of the industry and how is that being implemented throughout Latin America. And then we're going to position ourselves talking about the smart retrofitting activities and some of the initiatives as are presented, not only on the hard side of the business, as I call it, which is meaning, manufacturing, technology, machines, equipment, but also on the talent development, which is also supporting the normalization of the experience and the knowledge base of all the human resources, which are the ones operating the machines. So go ahead.
All right. Can you hear me very well? All right. So first of all, I would like to talk about the technology adoption in the different countries in Latin America, which we can notice in this chart that Brazil is the country who have more adoption of this type of technology. And we are going to understand why it's important to measure this type of metrics. So First of all, what are the transformative technology in Latin America, and what is the adoption that we already measured? For example, in the additive manufacturing in Mexico and Latin America, we are almost on the same level, which is we have a 1/3 of adoption, and right now is mainly focused in prototypes and very complex parts. Then we have generative design, which is created to elaborate different pieces with a very high complexity. And then we have automation, advance of cognitive automation. This is very important because due to COVID restrictions, this has been adapted by a lot of companies to maintain the stability, maintain quality, and also to keep the safe distance that we heard about it, you know. The next technology are the digital thread, digital twin, and blockchain, that all of those three are related of the same thing, which the first two are related to create a very safe, or create a trace of the information that's going to be saved in the third one is going to be the part who's going to protect all the data of the first two. The digital twin, we noticed that there is a technology which is most implemented in all Latin America, because right now we have a lot of solutions on the market that are displaying this type of technology. The next ones are the artificial intelligence, 5G, in regards to the communication and augmented reality. Those technologies are not well implemented on the industry because are more focused on face recognition and more soft solutions that are in the market right now. I don't know if you want to add something about in this.
Well, one of the things that we wanted to do through presenting what we call the transformative technologies was to really help you get a glance of what is the future of the normalization of the industry in regards to those things. So you see by the first three technologies, which have to do with hard, scientific implementation of technology, from additive manufacturing to cognitive automation. On that particular portion, we're talking about what are the hard facts and the implementation of those technologies. Additive is being implemented more and more on aftermarket parts, and really adding flexibility to some of those, oil and gas companies, to, even Ecopetrol or, Petrobras in Brazil or Pemex in Mexico are working on putting together those replacement parts, even in metal, so they can really have availability of those products when they have to replace some of those stations. And that is adding a new complexity to the ecosystem. The second portion has to do with the digital factory and the implementation of tools which are going to allow for faster response time, and then also the usage of the big data which is already floating around us. I call it the ether, all the data which is floating there, and then somebody has to be able to abstract that data and use it. And that's why, the blockchain, the digital thread, and all those technologies are going to allow us to really ramp up the process of implementation. When you talk to a lot of the big OEMs, which are producing consumer products from cars to appliance systems to digital to medical devices, you see that the complexity of the models and the change of the models and the platforms is really the process of developing and then launching and then usage, implementation, and then changing the life to a new model. It's being reduced from 7, 8, 9 years to now about 3 or 4 years. That means that there has to be much more flexibility, and that's what we were trying to reflect with this. Right? Go ahead, Daniel. Yeah.
All right. For the last one, the battery technology, which is right now there's a lot of research on this type of technologies and around the world, and we are hoping on the midterm, it's gonna be. There's going to be more solutions, more products with more efficiency.
And the game changer here has to do with the fact that the huge potential that Latin America has in regards to the reserves of lithium. You know, when you talk to people in Chile, Argentina, Mexico, you know, and even places in Peru and Colombia, you talk about the reserves of lithium. The key thing is not to export a commodity, but it's to really be able to transform that commodity and then add value and produce some of those, you know, battery containers and everything else related to the new technology. That's where the criticality is located, all right? So go ahead.
All right. So why we are thinking in smart retrofitting? The first, for the advantage that when the companies implement this type of procedures, or you have the advantage of the productivity increase, you can have a better quality, you have a reduce of dead time, and another advantage that you can have. So the smart retrofitting on the in America Latina is very common, like because the equipment which is installed on a lot of industry is more than 5 years or 10 to 15 years, and it's not just justifiable, because to replace to the new equipment, because if we get focused on the smart retrofitting, if we identify the devices which are very important on the equipment, we can increase capabilities, we can increase quality, we can increase a lot of things that are going to help you to be more efficient on the industry. So
over my work experience in the industry, you know, and as you heard what the lady explained, you know, I had a chance to work with Emerson Electric, a big industrial manufacturing, you know, parts producer, and also Cummins and the, you know, filtration systems and a bunch of different things, working in operations and in maintenance. If we had a fact or the capacity to really be able to reconfigure the old legacy systems that in many instances were already placed in the factories, and then being able to make them become more smarter or even way more intelligent, so we can get information from those things, that'll have the life of the maintenance manager way easier and way, you know, happier than what it used to be. Some of those solutions that we're going to be presenting here have to do with those actual applications which we see on the realm of the job shops, you know, or the manufacturing plants. One time, and then the other fact has to do with the robustness of some of that manufacturing technology, which has been produced by Italy, by Spain, by Brazil, by the United States, by Japan, Switzerland, and even Germany. One time I was visiting one of the end users that they had. It was called stamping on microfinish on micro components. And, you know, in visiting the plant, I ended up seeing a big mechanical press that had been in place and been in operations for the last 55 years. And basically what they did is that the whole infrastructure and the whole frame of the machine continues to work, but they had to be able to reconfigure the whole system by adding controls, by adding sensors, and then adding flexibility and productivity. So that machine was, and that was in reality, that was smart retrofitting done directly by the maintenance staff within the plant. So the fact that now the manufacturers and the OEMs are thinking about how to support those initiatives, and then Academy is also putting together and documenting some of those efforts, I think that's critical, and that's important. And those are some of the samples that Daniel's going to talk to you about in a minute. When you talk about manufacturing technology, which is the main consumption of those things, has to do with machining or metal coating or metal subtraction, and the other portion has to do with fabrication of metal components in the different materials. Go ahead.
Yeah, what sample that we are going to explain is retrofitting on metalworking, especially on CNC machining, in which we identify the 5 main topics or main devices on the CNC that you can improve to have a better results on the industry, which is the spindle. On the spindle, we come from the bearing, the lubrication, sealing, and cooling. And then the accessories that you can take in count, that's going to be the interconnectivity, that on experience from different industry, we notice and we already measure if you interconnect your equipment of the industry, you increase your efficiency in around 15 to 20%. So also there's a lot of solutions that you can implement, and also they are free for use. The protocols for like MT Connect that you don't have to pay any licensing, anything. As advanced software of CAD/CAM that make you the life very easy, and in the moment that you can transfer the designs to the CAM, and also ultrasonic machining and the MPA, which is the engineering department from AMT, who help to the companies or the person who's just interested in this to create the roadmap of technology of an implementation in the industry. So the first thing that we noticed that you can improve on the smart retrofitting metal working is the spindle. Why the spindle? Because it's the most expensive thing. It's the most important thing on the CNC machine. This type of spindles, you can do a lot of things that a lot of people do know. So you can increase revolution, you change the bearings, you can change the lubrication, you can change the coolant, and you can have a lot of benefits doing this type of things that we already saw implemented in a lot of industries.
At the end of the day, if you are an entrepreneur and you have an old machine where you were able to produce parts or cut parts at 3,000 RPMs, and then you want to be able to change one of the basic components, which is one of the second most expensive portions of the machine, one of them being the control and then the spindle, and that spindle is going to allow you to threefold the RPMs and be able to cut even way more exotic material. That's part of what we recommend with the retrofitting of spindle, right?
Yeah. After saying that, there's a lot of very important thing, which is the filtration system, which then on the market, and some of our members have a lot of solutions that you can increase the life of your tools, increase your life of the machine, the spindles, and everything. And these type of solution are everywhere. So, but a lot of people doesn't know that this type of exists. And instead of change the whole machine, you can adapt this type of technologies, and you can have better results like transfer.
And this has to do with the fact that in talking to Uniandes and Tec de Monterrey both, we discussed a lot, expanding the reach of the smart retrofitting not only from the actual machine itself, but also to the whole ecosystem which surrounds the machine, including auxiliary equipment. And when you're running in a machining operation, one of the things that you see is, and this also has to do with, the new EPA regulations and the ecology and the Save the Planet efforts and everything else. In many of the machining operations that you see around Latin America, you see that the oil, which is used as lubricant, to run the machines, it's not very well maintained, meaning that you have to change the whole system of oiling way more often than what is recommended. By adding, the filtration system, then you can really expand the life of the cutting tool, really protect the spindle, and at the same time, you're gonna be, having to dump or, throw or segregate in one place the oil, because you're gonna be able to use it way and way around just by adding this filtration, which is why we call it smart retrofitting.
Yeah, one other solution that we would like to talk is some pieces of wire holding that they can simulate a different axis, like at the fifth axis. So this type of devices can help you to increase your capabilities on the industry, and also reduce a lot of time for the characteristics of this type of devices.
One of the features of the supply chain in the Americas over the last 18 months, during COVID and even before COVID, because of the trade wars, is the normalization of the supply chains between Asia, Americas, and Europe. And one thing that you see is that there are a lot of global companies which are trying to find sourcing solutions in the whole Americas. In many instances, the job shops which are located in Latin America, from Colombia to Mexico and different places, might not have the capability because they're not able to run to the RPM which is needed. Or the second one they have no way of running a complex part which requires a fourth or a fifth axis. That's what you can do by retrofitting a system and adding, new work holding systems that allow you to simulate the fifth axis. So that's part of investment, smart investment to smart retrofitting. Go ahead.
And not only everything is related to the equipment, there's a lot of solutions that can impact direct on the workers and the factory. Like is the smart cleaning, air cleaning systems, which is Hastings, which is one of our members, that they produce a very smart equipment in which they are constantly monitoring the quality of the air, and they're gonna work when the different concentration of fumes or anything on the air is overpass some level, and they start to work. And this causes a lot of savings on energy and avoid a lot of healthy problems that the workers can have on the factory. All right.
Good.
One other thing or solution that we were talking is the MT Connect, which is a protocol, the free license that you don't need to pay anything. You just need to find Ethernet wiring and put your machine and install adapter and agent and start to communicate things. So it's simple like that. A lot of people don't know, but this is mainly focused on the new equipment. For the machines who are legacy, they don't have Ethernet ports or they don't have communication. There's a lot of devices that can be implemented of this machine, like external devices that is going to be wiring some electrical signals that's going to be from digital and analogical. And this type of models, it can be installed very easily, and they are already on the market. We already have a partner that we are going to talk this one, that they develop a lot of electronics and also software for solution for the company that you can create a project, a very complex, or you can create a project very simple that we're gonna see in the next slide. Do you want to?
Yeah, the whole of the colleagues throughout the conference have been talking about the digital factory. The digital factory is being able to interconnect your machines so you can really start catching up on productivity. You can really start analyzing the data that comes out of the machine, and you could really start making smarter decisions in some of the things and some of the readings that you're getting from the machine. One of the actual realities of living in Latin America is that most of those machines that are deployed throughout the ecosystem don't have interconnectivity by itself or native, because some of those machines have been in place for 17, 18, 19, 20 years. So either you go to the RS-232 or you go to the old, data transfer systems, which are very slow and which are not as complex or as broad as the new applications are. So in order for you to normalize ecosystems to getting information from the new machines that you might be adding to the factory, you can also add on new adapters or small pieces of hardware devices, which are going to allow you to make a machine communicate, the KPIs or the key data that you want to be able to extract. And then you can start making decisions. That's part of what we call the digital factory and the smart retrofitting, once again, by adding 1 or 2 or 3 components and taking advantage of the whole bench of the machine as it is. All right?
All right. So I want to talk a little bit about this project that is what relates. It was developed on last year's, along with a partner in Brazil, in which some students from this university make a very simple equipment, which is a induction motor. They made it smarter, and they already explain what they already do, and we're taking advantage of this, of what we are talking right now to mention this one, in which they install a sensor that's going to be monitoring the vibration of a motor, and they put this adapter, and they start to make it receive information and make it a little bit smarter. So those are as complex, as simple like this one, are the solutions that can be implemented on different equipment on the industry So this is a paradigm, some type of something for the industrial are scared because they think in new technology, they think that they need to spend a lot of money. Is not also that case. So this is a really good example of that.
Yeah, one of the things that we're going to be doing at the Feria Internacional de Bogotá, along with working with Uniandes and also with a large distributor from here, from Colombia, is that we're going to try to bring together a digital factory replicated throughout the show. That means that we're going to have compressors, plastic injectors, and a lot of machine manufacturing technology, which is going to be connected. So a lot of the end users and the consumers that have the idea that in order for them to interact or create a network within the factory, even if it's 5 machines, 10 machines, 15 machines, it's going to take a good amount of dollars or pesos, Colombian pesos. That's what we want to change in the mindset. You can start by connecting the 2 critical machines or the 2 critical processes which are critical to you, and then you can start expanding and growing from there once the savings justify the continued expansion of those things. And that's why, changing the idea that making your factory or your job shop become digital is a very expensive project. In working with local and organizations like Uniandes or Tec de Monterrey or different universities throughout Latin America, it's critical. That's part of what we've been doing, all right?
All right.
Good. Anything else?
All right. Okay, there's a lot of players which are changing the ecosystem. Well, this is another tendency which is coming from United States and Germany and different places that they are implementing these new technologies. They call it the ACE, which is artificial intelligence, additive manufacturing, advanced automation, and augmented reality, that this technology mainly are going to change the manufacturing floor of the industry, starting from the United States of different countries and then coming from Latin America.
You can start seeing that. One of the examples that we did not include here has to do with advanced automation. Not too long ago, about 3 months ago, we announced that we have just merged with a global organization that it's called Silicon Valley Robotics, which is basically about 250 different companies which are working on the next generation of robotics. And this is interesting because the way they introduce their company starts with a picture of an industrial robot, and it says, this is what you think of of robotics, something which is dirty, dumb, and bulky. And then they have another picture of one of those cobots, which is, smart, flexible, light, and you can really interact with it. So that's part of the change in the ecosystem that we see, that this is going to be changing the realm and how we do business and how some of those factors are implementing some of those technologies. And the other beauty is that the pricing in those things is really normalizing and coming up, down quite dramatically, as they are more and more being adopted throughout the industrial economies around the world, right?
So there are also a new business models that right now are working in the United States, which a lot of companies can take advantage because they don't need to have all the process in their company, and they can sublease different processes. This new tendency is called manufacturing as a service, manufacturing on demand, equipment as a service, special purpose acquisition, which you can rent by time. Can be one day, 1 week, one month. Special processes of this type of companies who rent their time for manufacturing products.
Right. And again, if you own a job shop, or you are consulting to a job shop owner, somebody that wants to expand the capacity and the complexity of the parts that they are able to manufacture, produce, form, fabricate, weld, whatever, they don't have, nowadays with these new platforms, they don't have to create the whole infrastructure or the whole technological capacity in order to be able to serve a market, because they can now start renting those things. The other beauty about these things is that there are now new platforms, which are basically like an app platform, somebody where your job shops, which are located in Chile, in Argentina, in Brazil, in Colombia, in Costa Rica, are able to, dump or load available hours and then explain that they have that capability, that knowledge, and they can do the work, the actual work for us. I was in a conference in Houston not too long ago, and I had a chance to talk to a gentleman from Guatemala, and that's what he was doing. He was doing it, this is quite interesting because it was an additive manufacturing company, and they were doing reverse engineering to a part, and then the actual manufacturing machine, additive manufacturing machine, they had it in Guatemala, but the whole reverse engineering was being done in the United States by the owner of this company living in Houston, sending the whole reverse engineering into the plant, and then they were producing those parts and then they're being sourced. So those are some of the new things which are happening in the ecosystem as we move. The other thing which is now changing, again, the face of what we see has to do with the usage of the digital applications. Some of those transformative technologies that we brought up, the incorporation of additive, not only to the prototyping, but also to the actual production of parts. And third, the robotic, as we pointed up, all right? And then we don't forget about materials, because materials is critical to all those things. You might have a very sophisticated manufacturing technology ecosystem, but if you don't have materials to react to those things, it's not gonna work. So now, more than anything, the simulation, the affordability of the materials, and the recyclability of the same, it's quite critical. And those are some of the things which we see that are going to be changing the way we do business. And also, when you incorporate smart retrofitting into your operations, have to take those things into consideration. Meaning what we discussed about, for example, the air moving systems on replacing some of those things. The reality of those things has to do with the fact that in the past, all those factories, if you go to a factory of motorcycles here in Colombia, for example, and you see the way they control the fumes is by having an exhaust system which is running all the time. If there are fumes, it's running, and it's taking the fumes out. If there's no fumes, it's still running, and that's just consuming energy. So those are some of the things which are now becoming, thinking about circular economy and also taking advantage of the oil and the rest of the scrap and a bunch of things. Go ahead. Yep. So where is all this technology deployed or displayed? There are two main events, as I said, and then there's one in Europe that just took place last year, which is basically EMO. That's where you find some of the new technologies. Then we have our own show, which is in Chicago this year, IMTS. And then there's also going to be a show in Colombia. Next one, please. Next one, which has to do with the Feria Internacional de Bogotá, which is taking place from the 26th to the 30th of September. And you're going to see a lot of those, new options and opportunities there. Okay. Finally, I want to talk about also an initiative of smart retrofitting that has to do with the hard part or the hardware of the whole ecosystem or the equation to be able to produce a manufactured part, but also the fact of the software which is used, or the soft or the human resources which are really touching and working and interacting with the machines and with the material and amongst themselves. And that's what we do, by adding and bringing up, a platform of e-learning. And that's part of what we've been discussing this week here in Colombia. The fact that there is a huge gap of knowledge between what the technical base is in Latin America and in the United States, in different places, to the actual need of knowledge, which is here. That's why we're bringing forward, some of those platforms, which is called e-learning. Those are learning modules in Spanish and in English that allow you to normalize the level of knowledge, so you can really make sure that whomever is dealing with the material or is measuring, assuring that the part is being measured correctly or the part is being transformed correctly, understands the whole process. And that's what we do through the e-learning platforms. All right. Finally, what Daniel was explaining a minute ago has to do with a service that we put together for the industry, which is called an assessment of what are the capabilities of manufacturing of all those facilities. This is where the smart retrofitting takes place, because some of the ideas or the solutions which are going to be introduced into those factories as part of the roadmap, the technology roadmap that we pointed out, had to do with doing some retrofitting, doing some digitalization, doing some interconnectivity, and finally replacing some of those old technologies that they might have there. All right? So with that, it's my pleasure to finish the conversation, opening up for questions and answers. Both Daniel and I will be happy to respond to any of your questions. You might have one or two. And thank you so much for your time, all right?
Thank you.